This figure shows pieces of a white substance which appear to be sublimating. To the right of these pieces are three graduated cylinders. Each cylinder holds a different color liquid, and above the liquid, the cylinders are filled with a fog-like substance. This fog-like substance swirls out of the top and around the outside of the cylinders. Figure 10. One solid carbon dioxide, dry ice, left, sublimes vigorously when placed in a liquid right, cooling the liquid and generating a dense mist of water above the cylinder. Credit Modification of work by Paul Flowers, Chapter Outline 10. 1 Intermolecular Forces 10. 2 Properties of Liquids 10. 3 Phase Transitions 10. 4 Phase Diagrams 10. 5 The Solid State of Matter 10. 6 Lattice Structures in Crystalline Solids. Leprosy has been a devastating disease throughout much of human history. Aside from the symptoms and complications of the illness, its social stigma led sufferers to be cast out of communities and isolated in colonies. In some regions, this practice lasted well into the 20th century. At that time, the best potential treatment for leprosy was oil from the chalmugra tree, but the oil was extremely thick, causing blisters and making usage painful and ineffective. Healthcare professionals seeking a better application contacted Alice Ball, a young chemist at the University of Hawaii, who had focused her master's thesis on a similar plant. Ball initiated a sequence of procedures, repeated acidification and purification to change the characteristics of the oil and isolate the active substances esters, discussed later in this text. The Ball method, as it later came to be called, became the standard treatment for leprosy for decades. In the liquid and solid states, atomic and molecular interactions are of considerable strength and play an important role in determining a number of physical properties of the substance. For example, the thickness or viscosity of the chalmugra oil was due to its intermolecular forces. In this chapter, the nature of these interactions and their effects on various physical properties of liquid and solid phases will be examined. Learning objectives: by the end of this section, you will be able to describe the types of intermolecular forces possible between atoms or molecules in condensed phases, dispersion forces, dipole-dipole attractions, and hydrogen bonding. Identify the types of intermolecular forces experienced by specific molecules based on their structures. Explain the relation between the intermolecular forces present within a substance and the temperatures associated with changes in its physical state, as was the case for gaseous substances. The kinetic molecular theory may be used to explain the behavior of solids and liquids. In the following description, the term particle will be used to refer to an atom, molecule, or ion. Note that we will use the popular phrase intermolecular attraction to refer to attractive forces between the particles of a substance, regardless of whether these particles are molecules, atoms, or ions. Consider these two aspects of the molecular level environments in solid, liquid, and gaseous matter. Particles in a solid are tightly packed together and often arranged in a regular pattern. In a liquid, they are close together with no regular arrangement. In a gas, they are far apart with no regular arrangement. Particles in a solid vibrate about fixed positions and do not generally move in relation to one another. In a liquid, they move past each other but remain in essentially constant contact. In a gas, they move independently of one another except when they collide. The differences in the properties of a solid, liquid, or gas reflect the strengths of the attractive forces between the atoms, molecules, or ions that make up each phase. The phase in which a substance exists depends on the relative extents of its intermolecular forces, IMFs, and the kinetic energies, Ke, of its molecules. IMFs are the various forces of attraction that may exist between the atoms and molecules of a substance due to electrostatic phenomena, as will be detailed in this module. These forces serve to hold particles close together, whereas the particles, Ke, provides the energy required to overcome the attractive forces and thus increase the distance between particles. Figure 10.2 illustrates how changes in physical state may be induced by changing the temperature, hence the average Ke of a given substance. 3 sealed flasks are labeled crystalline, solid, liquid, and gas from left to right. The first flask holds a cube composed of small spheres sitting on the bottom, while the second flask shows a lot of small spheres in the bottom that are spaced a small distance apart from one another and have lines around them to indicate motion. The third flask shows a few spheres spread far from one another with larger lines to indicate motion. There is a right-facing arrow that spans the top of all 3 flasks. The arrow is labeled increasing Ke temperature. There is a left-facing arrow that spans the bottom of all 3 flasks. The arrow is labeled increasing IMF. Figure 10. 2 transitions between solid, liquid, and gaseous states of a substance occur when conditions of temperature or pressure favor the associated changes in intermolecular forces. Note, the space between particles in the gas phase is much greater than shown. As an example of the processes depicted in this figure, consider a sample of water. When gaseous water is cooled sufficiently, the attractions between H2O molecules will be capable of holding them together when they come into contact with each other. The gas condenses, forming liquid H2O, for example. Liquid water forms on the outside of a cold glass as the water vapor in the air is cooled by the cold glass, as seen in Figure 10.3. Image A shows a brown-colored beverage in a glass with condensation on the outside. Image B shows a body of water with fog hovering above the surface of the water. Figure 10.3. Condensation forms when water vapor in the air is cooled enough to form liquid water, such as A, on the outside of a cold beverage glass, or B, in the form of fog. Credit A. Modification of work by Jenny Downing. Credit B. Modification of work by Corey Zanker. We can also liquefy many gases by compressing them, if the temperature is not too high. The increased pressure brings the molecules of a gas closer together, such that the attractions between the molecules become strong relative to their Ke. Consequently, they form liquids. Butane, C4H10, is the fuel used in disposable lighters and is a gas at standard temperature and pressure. Inside the lighter's fuel compartment, the butane is compressed to a pressure that results in its condensation to the liquid state, as shown in Figure 10.4. A butane lighter is shown. Figure 10.4. Gaseous butane is compressed within the storage compartment of a disposable lighter, resulting in its condensation to the liquid state. Credit. Modification of work by Samcat/Flicker. Finally, if the temperature of a liquid becomes sufficiently low, or the pressure on the liquid becomes sufficiently high, the molecules of the liquid no longer have enough Ke to overcome the IMF between them, and a solid forms. A more thorough discussion of these and other changes of state, or phase transitions, is provided in a later module of this chapter. Link to learning. Access this interactive simulation on states of matter, phase transitions, and intermolecular forces. This simulation is useful for visualizing concepts introduced throughout this chapter. Forces between molecules under appropriate conditions. The attractions between all gas molecules will cause them to form liquids or solids. This is due to intermolecular forces, not intramolecular forces. Intramolecular forces are those within the molecule that keep the molecule together, for example, the bonds between the atoms. Intermolecular forces are the attractions between molecules, which determine many of the physical properties of a substance. Figure 10.5 illustrates these different molecular forces. The strengths of these attractive forces vary widely, though usually the IMFs between small molecules are weak compared to the intramolecular forces that bond atoms together within a molecule. For example, to overcome the IMFs in 1 mole of liquid HCl and convert it into gaseous HCl requires only about 17 kilojoules. However, To break the covalent bonds between the hydrogen and chlorine atoms in 1 mole of HCl requires about 25 times more energy, 430 kilojoules. An image is shown in which two molecules composed of a green sphere labeled Cl, connected on the right to a white sphere labeled H, are near one another with a dotted line labeled intermolecular force, weak, drawn between them. A line connects the two spheres in each molecule, and the line is labeled intramolecular force, strong. Figure 10. 5 intramolecular forces keep a molecule intact. Intermolecular forces hold multiple molecules together and determine many of a substance's properties. All of the attractive forces between neutral atoms and molecules are known as van der Waals forces, although they are usually referred to more informally as intermolecular attraction. We will consider the various types of IMFs in the next 3 sections of this module. Dispersion forces, one of the 3 van der Waals forces, is present in all condensed phases, regardless of the nature of the atoms or molecules composing the substance. This attractive force is called the London dispersion force in honor of German-born American physicist Fritz London, who, in 1928, first explained it. This force is often referred to as simply the dispersion force. Because the electrons of an atom or molecule are in constant motion, or, alternatively, the electron's location is subject to quantum mechanical variability. At any moment in time, an atom or molecule can develop a temporary, instantaneous dipole if its electrons are distributed asymmetrically. The presence of this dipole can, in turn, distort the electrons of a neighboring atom or molecule, producing an induced dipole. These two rapidly fluctuating, temporary dipoles thus result in a relatively weak electrostatic attraction between the species, a so-called dispersion force like that illustrated in Figure 10. 6. 2 pairs of molecules are shown where each molecule has one larger blue side labeled delta sign, negative sign, and a smaller red side labeled delta sign, positive sign. Toward the middle of the both molecules, but still on each distinct side, is a black dot. Between the two images is a dotted line labeled attractive force. In the first image, the red and blue sides are labeled unequal distribution of electrons. Below both images are brackets. The brackets are labeled temporary dipoles. Figure 10. 6 dispersion forces result from the formation of temporary dipoles, as illustrated here for 2 nonpolar diatomic molecules. Dispersion forces that develop between atoms in different molecules can attract the 2 molecules to each other. The forces are relatively weak, however, and become significant only when the molecules are very close. Larger and heavier atoms and molecules exhibit stronger dispersion forces than do smaller and lighter atoms and molecules. F2 and Cl2 are gases at room temperature, reflecting weaker attractive forces. Br2 is a liquid, and I2 is a solid, reflecting stronger attractive forces. Trends in observed melting and boiling points for the halogens clearly demonstrate this effect, as seen in Table 10. 1. Melting and boiling points of the halogens: halogen molar mass, atomic radius, melting point, boiling point. Fluorine F238 G/mol, 72 ppm 53 K85 K. Chlorine Cl271 G/mol, 99 ppm 172 K238 K. Bromine Br2 160 G/mol, 114 ppm 266 K. 332 K. Iodine I2 254 G/mol, 133 ppm 387 K. 457 K. Astatine at 2 420 G/mol, 150 ppm 575 K. 610 K. Table 10. 1. The increase in melting and boiling points with increasing atomic molecular size may be rationalized by considering how the strength of dispersion forces is affected by the electronic structure of the atoms or molecules in the substance. In a larger atom, the valence electrons are, on average, farther from the nuclei than in a smaller atom. Thus, they are less tightly held and can more easily form the temporary dipoles that produce the attraction. The measure of how easy or difficult it is for another electrostatic charge, for example, a nearby ion or polar molecule, to distort a molecule's charge distribution, its electron cloud, is known as polarizability. A molecule that has a charge cloud that is easily distorted is said to be very polarizable and will have large dispersion forces. One with a charge cloud that is difficult to distort is not very polarizable and will have small dispersion forces. Example 10. 1 London forces and their effects order the following compounds of a group 14 element and hydrogen from lowest to highest boiling point: CH4, CH4, GH4, and SNH4. Explain your reasoning. Solution applying the skills acquired in the chapter on chemical bonding and molecular geometry. All of these compounds are predicted to be nonpolar, so they may experience only dispersion forces. The smaller the molecule, the less polarizable and the weaker the dispersion forces. The larger the molecule, the larger the dispersion forces. The molar masses of CH4, CH4, GH4, and SNH4 are approximately 16 g/mol, 32 g/mol, 77 g/mol, and 123 g/mol, respectively. Therefore, CH4 is expected to have the lowest boiling point, and SNH for the highest boiling point. The ordering from lowest to highest boiling point is expected to be CH4, CH4, GH4, SNH4. A graph of the actual boiling points of these compounds versus the period of the group 14 element shows this prediction to be correct. A line graph, titled Carbon Family, is shown where the y-axis is labeled temperature, degree sign C, and has values of -200 to -40 from bottom to top in increments of 20. The x-axis is labeled period and has values of 0 to 5 in increments of 1. The first point on the graph is labeled CH subscript 4 and is at point 2, -160. The second point on the graph is labeled SIH subscript 4 and is at point 3, -120, while the third point on the graph is labeled GEH subscript 4 and is at point 4, -100. The fourth point on the graph is labeled SNH subscript 4 and is at point 5, -60. Check your learning. Order the following hydrocarbons from lowest to highest boiling point: C2H6, C3H8, and C4H10. Answer: C2H6, C3H8, C4H10. All of these compounds are nonpolar and only have London dispersion forces. The larger the molecule, the larger the dispersion forces, and the higher the boiling point. The ordering from lowest to highest boiling point is therefore C2H6, C3H8, C4H10. The shapes of molecules also affect the magnitudes of the dispersion forces between them. For example, boiling points for the isomers N-pentane, isopentane, and neopentane, shown in Figure 10.7, are 36 degrees C, 27 degrees C, and 95 degrees C, respectively. Even though these compounds are composed of molecules with the same chemical formula, C5H12, the difference in boiling points suggests that dispersion forces in the liquid phase are different, being greatest for N-pentane and least for neopentane. The elongated shape of N-pentane provides a greater surface area available for contact between molecules, resulting in correspondingly stronger dispersion forces. The more compact shape of isopentane offers a smaller surface area available for intermolecular contact, and therefore weaker dispersion forces. Neopentane molecules are the most compact of the three, offering the least available surface area for intermolecular contact and hence the weakest dispersion forces. This behavior is analogous to the connections that may be formed between strips of Velcro brand fasteners. The greater the area of the strip's contact, the stronger the connection. Three images of molecules are shown. The first shows a cluster of large gray spheres each bonded together and to several smaller white spheres. There is a gray, jagged line, and then the mirror image of the first cluster of spheres is shown. Above these two clusters is the label, small contact area, weakest attraction, and below is the label, neopentyne boiling point, 95 degrees C. The second shows a chain of three gray spheres bonded by the middle sphere to a fourth gray sphere. Each gray sphere is bonded to several smaller white spheres. There is a jagged gray line and then the mirror image of the first chain appears. Above these two chains is the label, less surface area, less attraction, and below is the label, isopentyne boiling point, 27 degrees C. The third image shows a chain of five gray spheres bonded together and to several smaller white spheres. There is a jagged gray line, and then the mirror image of the first chain appears. Above these chains is the label, large contact area, strong attraction, and below is the label, neopentyne boiling point 36 degrees C, figure 10. 7. The strength of the dispersion forces increases with the contact area between molecules, as demonstrated by the boiling points of these pentane isomers. Chemistry in everyday life. Geckos and intermolecular forces. Geckos have an amazing ability to adhere to most surfaces. They can quickly run up smooth walls and across ceilings that have no toe holds, and they do this without having suction cups or a sticky substance on their toes. And while a gecko can lift its feet easily as it walks along a surface, if you attempt to pick it up, it sticks to the surface. How are geckos, as well as spiders and some other insects, able to do this? Although this phenomenon has been investigated for hundreds of years, scientists only recently uncovered the details of the process that allows geckos' feet to behave this way. Geckos' toes are covered with hundreds of thousands of tiny hairs known as setae, with each seta, in turn, branching into hundreds of tiny, flat, triangular tips called spatulae. The huge numbers of spatulae on its setae provide a gecko, shown in figure 10.8, with a large total surface area for sticking to a surface. In 2000, Keller Autumn, who leads a multi-institutional gecko research team, found that geckos adhered equally well to both polar silicon dioxide and non-polar gallium arsenide. This proved that geckos stick to surfaces because of dispersion forces, weak intermolecular attractions arising from temporary, synchronized charge distributions between adjacent molecules. Although dispersion forces are very weak, the total attraction over millions of spatulae is large enough to support many times the gecko's weight. In 2014, two scientists developed a model to explain how geckos can rapidly transition from sticky to non-sticky. Alex Greene and Kung Hu at Oregon State University described how geckos can achieve this by changing the angle between their spatulae and the surface. Geckos' feet, which are normally non-sticky, become sticky when a small shear force is applied. By curling and uncurling their toes, geckos can alternate between sticking and unsticking from a surface, and thus easily move across it. Later research led by Alyssa Stark at University of Akron showed that geckos can maintain their hold on hydrophobic surfaces, similar to the leaves in their habitats, equally well whether the surfaces were wet or dry. Stark's experiment used a ribbon to gently pull the geckos until they slipped, so that the researchers could determine the gecko's ability to hold various surfaces under wet and dry conditions. Further investigations may eventually lead to the development of better adhesives and other applications. Three figures are shown. The first is a photo of the bottom of a gecko's foot. The second is a bigger version which shows the setae. The third is a bigger version of the setae and shows the spatulae. Figure 10. 8 geckos' toes contain large numbers of tiny hairs setae, which branch into many triangular tips, spatulae. Geckos adhere to surfaces because of van der Waals attractions between the surface and a gecko's millions of spatulae. By changing how the spatulae contact the surface, Geckos can turn their stickiness on and off. Credit photo. Modification of work by JC*+A. /Flickr link to learning. Watch this video to learn more about Keller-Autumn's research that determined that van der Waals forces are responsible for a gecko's ability to cling and climb. Dipole-dipole attractions. Recall from the chapter on chemical bonding and molecular geometry that polar molecules have a partial positive charge on one side and a partial negative charge on the other side of the molecule, a separation of charge called a dipole. Consider a polar molecule such as hydrogen chloride, HCl. In the HCl molecule, the more electronegative Cl atom bears the partial negative charge, whereas the less electronegative H atom bears the partial positive charge. An attractive force between HCl molecules results from the attraction between the positive end of one HCl molecule and the negative end of another. This attractive force is called a dipole-dipole attraction, the electrostatic force between the partially positive end of one polar molecule and the partially negative end of another, as illustrated in Figure 10.9. Two pairs of molecules are shown where each molecule has one larger blue side labeled delta sign, negative sign, and a smaller red side labeled delta sign, positive sign. In the first pair, the red sides of the two molecules both face to the left and the blue side to the right. A horizontal dotted line lies in between the two. In the second pair, the molecules face up and down, with the red and blue ends aligning. A horizontal dotted line lies between the red and blue ends facing upward and another lies between the red and blue ends facing downward. Figure 10.9. This image shows two arrangements of polar molecules, such as HCl, that allow an attraction between the partial negative end of one molecule and the partial positive end of another. The effect of a dipole-dipole attraction is apparent when we compare the properties of HCl molecules to nonpolar F2 molecules. Both HCl and F2 consist of the same number of atoms and have approximately the same molecular mass. At a temperature of 150 K, molecules of both substances would have the same average Ke. However, the dipole-dipole attractions between HCl molecules are sufficient to cause them to stick together to form a liquid, whereas the relatively weaker dispersion forces between nonpolar F2 molecules are not, and so this substance is gaseous at this temperature. The higher normal boiling point of HCl, 188 K, compared to F2, 85 K, is a reflection of the greater strength of dipole-dipole attractions between HCl molecules compared to the attractions between nonpolar F2 molecules. We will often use values such as boiling or freezing points, or enthalpies of vaporization or fusion, as indicators of the relative strengths of IMFs of attraction present within different substances. Example 10. Two dipole-dipole forces and their effects predict which will have the higher boiling point, N2 or Co. Explain your reasoning. Solution: Co and N2 are both diatomic molecules with masses of about 28 AMU, so they experience similar London dispersion forces. Because Co is a polar molecule, it experiences dipole-dipole attractions. Because N2 is nonpolar, its molecules cannot exhibit dipole-dipole attractions. The dipole-dipole attractions between Co molecules are comparably stronger than the dispersion forces between nonpolar N2 molecules, so Co is expected to have the higher boiling point. Check your learning. Predict which will have the higher boiling point, Eichel or Br2. Explain your reasoning. Answer: Eichel. Eichel and Br2 have similar masses, 160 AMU, and therefore experience similar London dispersion forces. Eichel is polar and thus also exhibits dipole-dipole attractions. Br2 is nonpolar and does not. The relatively stronger dipole-dipole attractions require more energy to overcome, so Eichel will have the higher boiling point. Hydrogen bonding nitrosyl fluoride ONF, molecular mass 49 AMU, is a gas at room temperature. Water H2O, molecular mass 18 AMU, is a liquid, even though it has a lower molecular mass. We clearly cannot attribute this difference between the two compounds to dispersion forces. Both molecules have about the same shape, and ONF is the heavier and larger molecule. It is, therefore, expected to experience more significant dispersion forces. Additionally, we cannot attribute this difference in boiling points to differences in the dipole moments of the molecules. Both molecules are polar and exhibit comparable dipole moments. The large difference between the boiling points is due to a particularly strong dipole-dipole attraction that may occur when a molecule contains a hydrogen atom bonded to a fluorine, oxygen, or nitrogen atom, the three most electronegative elements. The very large difference in electronegativity between the H atom, 2,1, and the atom to which it is bonded, 4,0 for an F atom, 3,5 for an O atom, or 3,0 for an N atom, combined with the very small size of a H atom and the relatively small sizes of F, O, or N atoms, leads to highly concentrated partial charges with these atoms. Molecules with FH, OH, or NH moieties are very strongly attracted to similar moieties in nearby molecules, a particularly strong type of dipole-dipole attraction called hydrogen bonding. Examples of hydrogen bonds include HF-HF, H2O-HO, and H3NHNH2, in which the hydrogen bonds are denoted by dots. Figure 10. 10 illustrates hydrogen bonding between water molecules. 5 water molecules are shown near one another, but not touching. A dotted line lies between many of the hydrogen atoms on one molecule and the oxygen atom on another molecule. Figure 10. 10 water molecules participate in multiple hydrogen bonding interactions with nearby water molecules. Despite use of the word bond, keep in mind that hydrogen bonds are intermolecular attractive forces, not intramolecular attractive forces, covalent bonds. Hydrogen bonds are much weaker than covalent bonds, only about 5 to 10% as strong, but are generally much stronger than other dipole-dipole attractions and dispersion forces. Hydrogen bonds have a pronounced effect on the properties of condensed phases, liquids, and solids. For example, consider the trends in boiling points for the binary hydrides of group 15, NH3, pH3, as H3 and SbH3. Group 16 hydrides H2O, H2S, H2C, and H2T, and Group 17 hydrides HF, HCl, HBr, and HI. The boiling points of the heaviest 3 hydrides for each group are plotted in Figure 10. 11. As we progress down any of these groups, the polarities of the molecules decrease slightly, whereas the sizes of the molecules increase substantially. The effect of increasingly stronger dispersion forces dominates that of increasingly weaker dipole-dipole attractions, and the boiling points are observed to increase steadily. A line graph is shown where the y-axis is labeled boiling point, degree sign C, and has values of -150 to 150 from bottom to top in increments of 50. The x-axis is labeled period and has values of 0 to 5 in increments of 1. 3 lines are shown on the graph and are labeled in the legend. The red line is labeled as halogen family, the blue is oxygen family, and the green is nitrogen family. The first point on the red line is labeled question mark and is at point 2, -120. The second point on the line is labeled HCl and is at point 3, -80, while the third point on the line is labeled HBr and is at point 4, -60. The fourth point on the line is labeled HI and is at point 5, -40. The first point on the green line is labeled question mark and is at point 2, -125. The second point on the line is labeled pH, subscript 3, and is at point 3, -80, while the third point on the line is labeled a SH, subscript 3, and is at point 4, -55. The fourth point on the line is labeled SBH, subscript 3, and is at point 5, -10. The first point on the blue line is labeled question mark and is at point 2, -80. The second point on the line is labeled H, subscript 2s, and is at point 3, -55, while the third point on the line is labeled H, subscript 2se, and is at point 4, -45. The fourth point on the line is labeled H, subscript 2te, and is at point 5, -3. Figure 10. 11 for the group 15, 16, and 17 hydrides. The boiling points for each class of compounds increase with increasing molecular mass for elements in periods 3, 4, and 5. If we use this trend to predict the boiling points for the lightest hydride for each group, we would expect NH3 to boil at about -120 C, H2O to boil at about -80 degrees C, and HF to boil at about -110 degrees C. However, when we measure the boiling points for these compounds, we find that they are dramatically higher than the trends would predict, as shown in Figure 10. 12. The stark contrast between our naive predictions and reality provides compelling evidence for the strength of hydrogen bonding. A line graph is shown where the y-axis is labeled boiling point, degree sign, C, and has values of -150 to 150 from bottom to top in increments of 50. The x-axis is labeled period and has values of 0 to 5 in increments of 1. 3 lines are shown on the graph and are labeled in the legend. The red line is labeled as halogen family, the blue is oxygen family, and the green is nitrogen family. The first point on the red line is labeled HF and is at point 225. The second point on the line is labeled HCl and is at point 3, -80, while the third point on the line is labeled HBr and is at point 4, -60. The fourth point on the line is labeled HI and is at point 5, -40. The first point on the green line is labeled NH, subscript 3, and is at point 2, -40. The second point on the line is labeled pH, subscript 3, and is at point 3, -80, while the third point on the line is labeled a SH, subscript 3, and is at point 4, -55. The fourth point on the line is labeled SBH, subscript 3, and is at point 5, -10. The first point on the blue line is labeled H, subscript 2, O, and is at point 2, 100. The second point on the line is labeled H, subscript 2, S, and is at point 3, -55, while the third point on the line is labeled H, subscript 2, SE, and is at point 4, -45. The fourth point on the line is labeled H, subscript 2, TE, and is at point 5, -3. Figure 10. 12 in comparison to periods 3-5, the binary hydrides of period 2 elements in groups 17, 16, and 15, F, O, and N, respectively, exhibit anomalously high boiling points due to hydrogen bonding. Example 10. 3 effect of hydrogen bonding on boiling points. Consider the compounds dimethyl, CH3OCH3, ethanol, CH3CH2OH, and propane, CH3CH2CH3. Their boiling points, not necessarily in order, are -42, 1 degrees C -24, 8 degrees C, and 78.4 degrees C. Match each compound with its boiling point. Explain your reasoning. Solution: the VSEPR predicted shapes of CH3OCH3, CH3CH2OH, and CH3CH2CH3 are similar, as are their molar masses, 46 g/mol, 46 g/mol, and 44 g/mol, respectively, so they will exhibit similar dispersion forces. Since CH3CH2CH3 is nonpolar, it may exhibit only dispersion forces. Because CH3OCH3 is polar, it will also experience dipole-dipole attractions. Finally, CH3CH2OH has a -O group, and so it will experience the uniquely strong dipole-dipole attraction known as hydrogen bonding. So the ordering in terms of strength of IMFs, and thus boiling points, is CH3CH to CH3, CH3OCH3, CH3CH2OH. The boiling point of propane is -42. 1 degrees C, the boiling point of dimethyl is -24, 8 degrees C, and the boiling point of ethanol is 78, 5 degrees C. Check your learning. Ethane, CH3CH3, has a melting point of -183 degrees C and a boiling point of -89 degrees C. Predict the melting and boiling points for methylamine, CH3NH2. Explain your reasoning. Answer: the melting point and boiling point for methylamine are predicted to be significantly greater than those of ethane. CH3CH3 and CH3NH2 are similar in size and mass, but methylamine possesses an -NH group and therefore may exhibit hydrogen bonding. This greatly increases its IMFs and therefore its melting and boiling points. It is difficult to predict values, but the known values are a melting point of -93 degrees C and a boiling point of -6 degrees C. How sciences interconnect hydrogen bonding and DNA, deoxyribonucleic acid, DNA, is found in every living organism and contains the genetic information that determines the organism's characteristics, provides the blueprint for making the proteins necessary for life, and serves as a template to pass this information on to the organism's offspring. A DNA molecule consists of two anti-parallel chains of repeating nucleotides, which form its well-known double helical structure, as shown in Figure 10.13. Two images are shown. The first lies on the left side of the page and shows a helical structure like a twisted ladder where the rungs of the ladder, labeled base pair, are red, yellow, green, and blue paired bars. The red and yellow bars, which are always paired together, are labeled in the legend, which is titled nitrogenous bases as adenine and thymine, respectively. The blue and green bars, which are always paired together, are labeled in the legend as guanine and cytosine, respectively. At the top of the helical structure, the left-hand side rail, or sugar-phosphate backbone, is labeled as 3', while the right is labeled as 5'. These labels are reversed at the bottom of the helix. To the right of the page is a large Lewis structure. The top left corner of this structure, labeled 5', shows a phosphorus atom single bonded to 3 oxygen atoms, one of which has a superscripted negative charge, and double bonded to a 4th oxygen atom. One of the single bonded oxygen atoms is single bonded to the left corner of a 5-membered ring, with an oxygen atom at its top point, and which is single bonded to an oxygen atom on the bottom left. This oxygen atom is single bonded to a phosphorus atom that is single bonded to 2 other hydrogen atoms, and double bonded to a 4th oxygen atom. The lower left of these oxygen atoms is single bonded to another oxygen atom that is single bonded to a 5-membered ring, with an oxygen in the upper bonding site. The bottom left of this ring has a hydroxyl group attached to it, while the upper right carbon is single bonded to a nitrogen atom that is part of a 5-membered ring bonded to a 6-membered ring. Both of these rings have points of unsaturation and nitrogen atoms bonded into their structures. On the right side of the 6-membered ring are 2 single-bonded amine groups and a double-bonded oxygen. 3 separate dotted lines extend from these sites to corresponding sites on a second 6-membered ring. This ring has points of unsaturation and a nitrogen atom in the bottom right bonding position that is single bonded to a 5-membered ring on the right side of the image. This ring is single bonded to a carbon that is single bonded to an oxygen that is single bonded to a phosphorus. The phosphorus is single bonded to 2 other oxygen atoms and double bonded to a 4th oxygen atom. This group is labeled 5'. The 5-membered ring is also bonded on the top side to an oxygen that is bonded to a phosphorus single, bonded to 2 other oxygen atoms, and double bonded to a 4th oxygen atom. The upper left oxygen of this group is single bonded to a carbon that is single bonded to a 5-membered ring, with an oxygen in the bottom bonding position. This ring has a hydroxyl group on its upper right side that is labeled 3' and is bonded on the left side to a nitrogen that is a member of a 5-membered ring. This ring is bonded to a 6-membered ring, and both have points of unsaturation. This ring has a nitrogen on the left side, as well as an amine group that have 2 dotted lines leading from them to an oxygen and amine group on a 6-membered ring. These dotted lines are labeled hydrogen bonds. The 6-membered ring also has a double-bonded oxygen on its lower side and a nitrogen atom on its left side that is single-bonded to a 5-membered ring. This ring connects to the 2 phosphate groups mentioned at the start of this to form a large circle. The name guanine is written below the lower left side of this image, while the name cytosine is written on the lower right. The name thymine is written above the right side of the image, and adenine is written on the top right. 3 sections are indicated below the images where the left is labeled sugar-phosphate backbone, the middle is labeled bases, and the right is labeled sugar-phosphate backbone. Figure 10. 2 separate DNA molecules form a double-stranded helix in which the molecules are held together via hydrogen bonding. Credit: modification of work by Jerome Walker, Dennis Mitz. Each nucleotide contains a deoxyribose sugar bound to a phosphate group on one side and one of 4 nitrogenous bases on the other. 2 of the bases, cytosine C and thymine T, are single-ringed structures known as pyrimidines. The other 2, adenine A and guanine G, are double-ringed structures called purines. These bases form complementary base pairs consisting of 1 purine and 1 pyrimidine, with adenine pairing with thymine and cytosine with guanine. Each base pair is held together by hydrogen bonding. A and T share 2 hydrogen bonds, C and G share 3, and both pairings have a similar shape and structure. Figure 10. 14. A large Lewis structure is shown. The top left corner of this structure, labeled 5', shows a phosphorus atom single bonded to 3 oxygen atoms, one of which has a superscripted negative charge, and double bonded to a 4th oxygen atom. One of the single bonded oxygen atoms is single bonded to the left corner of a 5-membered ring with an oxygen atom at its top point, and which is single bonded to an oxygen atom on the bottom left. This oxygen atom is single bonded to a phosphorus atom that is single bonded to 2 other hydrogen atoms and double bonded to a 4th oxygen atom. The lower left of these oxygen atoms is single bonded to another oxygen atom that is single bonded to a 5-membered ring with an oxygen in the upper bonding site. The bottom left of this ring has a hydroxyl group attached to it, while the upper right carbon is single bonded to a nitrogen atom that is part of a 5-membered ring bonded to a 6-membered ring. Both of these rings have points of unsaturation and nitrogen atoms bonded into their structures. On the right side of the 6-membered ring are 2 single-bonded amine groups and a double-bonded oxygen. 3 separate dotted lines extend from these sites to corresponding sites on a second 6-membered ring. This ring has points of unsaturation and a nitrogen atom in the bottom right bonding position that is single bonded to a 5-membered ring on the right side of the image. This ring is single bonded to a carbon that is single bonded to an oxygen that is single bonded to a phosphorus. The phosphorus is single bonded to 2 other oxygen atoms and double bonded to a 4th oxygen atom. This group is labeled 5'. The 5-membered ring is also bonded on the top side to an oxygen that is bonded to a phosphorus single, bonded to 2 other oxygen atoms, and double bonded to a 4th oxygen atom. The upper left oxygen of this group is single bonded to a carbon that is single bonded to a 5-membered ring, with an oxygen in the bottom bonding position. This ring has a hydroxyl group on its upper right side that is labeled 3', and is bonded on the left side to a nitrogen that is a member of a 5-membered ring. This ring is bonded to a six-membered ring, and both have points of unsaturation. This ring has a nitrogen on the left side, as well as an amine group that have two dotted lines leading from them to an oxygen and amine group on a six-membered ring. These dotted lines are labeled hydrogen bonds. The six-membered ring also has a double-bonded oxygen on its lower side and a nitrogen atom on its left side that is single-bonded to a five-membered ring. This ring connects to the two phosphate groups mentioned at the start of this to form a large circle. The name guanine is written below the lower left side of this image, while the name cytosine is written on the lower right. The name thymine is written above the right side of the image, and adenine is written on the top right. Three sections are indicated below the images where the left is labeled sugar-phosphate backbone, the middle is labeled bases, and the right is labeled sugar-phosphate backbone. Figure 10.14. The geometries of the base molecules result in maximum hydrogen bonding between adenine and thymine AT, and between guanine and cytosine GC, so-called complementary base pairs. The cumulative effect of millions of hydrogen bonds effectively holds the two strands of DNA together. Importantly, the two strands of DNA can relatively easily unzip down the middle since hydrogen bonds are relatively weak compared to the covalent bonds that hold the atoms of the individual DNA molecules together. This allows both strands to function as a template for replication. Learning objectives. By the end of this section, you will be able to distinguish between adhesive and cohesive forces, define viscosity, surface tension, and capillary rise, describe the roles of intermolecular attractive forces in each of these properties. Phenomena. When you pour a glass of water or fill a car with gasoline, you observe that water and gasoline flow freely. But when you pour syrup on pancakes or add oil to a car engine, you note that syrup and motor oil do not flow as readily. The viscosity of a liquid is a measure of its resistance to flow. Water, gasoline, and other liquids that flow freely have a low viscosity. Honey, syrup, motor oil, and other liquids that do not flow freely, like those shown in Figure 10.15, have higher viscosities. We can measure viscosity by measuring the rate at which a metal ball falls through a liquid. The ball falls more slowly through a more viscous liquid, or by measuring the rate at which a liquid flows through a narrow tube. More viscous liquids flow more slowly. Two photographs are shown and labeled A and B. Photo A shows a jar of honey with a dipper drizzling it onto a biscuit. More biscuits are shown in a basket in the background. Photo B shows the engine of a car and a person adding motor oil to the engine. Figure 10.15. A. Honey and B. Motor oil are examples of liquids with high viscosities. They flow slowly. Credit A. Modification of work by Scott Bauer. Credit B. Modification of work by David Nagy. The IMFs between the molecules of a liquid, the size and shape of the molecules, and the temperature determine how easily a liquid flows. As Table 10.2 shows, the more structurally complex are the molecules in a liquid and the stronger the IMFs between them, the more difficult it is for them to move past each other, and the greater is the viscosity of the liquid. As the temperature increases, the molecules move more rapidly, and their kinetic energies are better able to overcome the forces that hold them together. Thus, the viscosity of the liquid decreases. Viscosities of common substances at 25 degrees C. Substance formula. Viscosity M-Pa-S. Water H2O0. 890 mercury Hg1. 526 ethanol C2H, 50H 174 octane C8H180. 508 ethylene glycol CH2, OCH2, O16. 1 honey variable (2, 00010, 000 motor oil variable. Table 10.2. The various IMFs between identical molecules of a substance are examples of cohesive forces. The molecules within a liquid are surrounded by other molecules, and are attracted equally in all directions by the cohesive forces within the liquid. However, the molecules on the surface of a liquid are attracted only by about one-half as many molecules. Because of the unbalanced molecular attractions on the surface molecules, liquids contract to form a shape that minimizes the number of molecules on the surface. That is, the shape with the minimum surface area. A small drop of liquid tends to assume a spherical shape, as shown in Figure 10.16, because in a sphere, the ratio of surface area to volume is at a minimum. Larger drops are more greatly affected by gravity, air resistance, surface interactions, and so on, and as a result, are less spherical. A photo of a spider's web with droplets of water attached to it is shown. Two images are shown. The right of the photo and arrows lead from the photo to the images. The upper image shows 28 blue spheres stacked one atop the other in the bottom of a circular background. 5 arrows are drawn pointing to the sides and downward from the sphere in the top middle of the drawing. The lower image shows another circular background of the same size as the first, but this time the blue spheres fill the image and are packed closely together. A sphere in the middle has 6 arrows pointing in all directions away from it. Figure 10.16 attractive forces result in a spherical water drop that minimizes surface area. Cohesive forces hold the sphere together. Adhesive forces keep the drop attached to the web. Credit photo. Modification of work by Audiobook. Flicker. Surface tension is defined as the energy required to increase the surface area of a liquid, or the force required to increase the length of a liquid surface by a given amount. This property results from the cohesive forces between molecules at the surface of a liquid, and it causes the surface of a liquid to behave like a stretched rubber membrane. Surface tensions of several liquids are presented in Table 10.3. Among common liquids, water exhibits a distinctly high surface tension due to strong hydrogen bonding between its molecules. As a result of this high surface tension, the surface of water represents a relatively tough skin that can withstand considerable force without breaking. A steel needle carefully placed on water will float. Some insects, like the one shown in Figure 10.17, even though they are denser than water, move on its surface because they are supported by the surface tension. Surface tensions of common substances at 25 degrees C. Substance formula: surface tension, MnM, water H2O 71, 99 mercury Hg 458, 48 ethanol C2H5 OH21, 97 octane C8H 1821, 14 ethylene glycol CH2 OCH2 O47, 99 Table 10.3. A photo and a diagram as shown, and a right-facing arrow leads from the photo to the image. The photo shows an insect standing on the surface of a sample of water. The image shows a square background that is 2/3 covered in blue spheres that are closely packed together. A brown line starts at the upper left corner of the background and rests on top of the first row of spheres. The sphere directly under this low point of the line has 4 arrows drawn on it that face to both sides and downward. A sphere in the bottom center of the image has 6 arrows drawn on it that all face outward in different directions. Figure 10.17 surface tension, right, prevents this insect, a water strider, from sinking into the water. Surface tension is affected by a variety of variables, including the introduction of additional substances on the surface. In the late 1800s, Agnes Pockels, who was initially blocked from pursuing a scientific career but studied on her own, began investigating the impact and characteristics of soapy and greasy films in water. Using homemade materials, she developed an instrument known as a trough for measuring surface contaminants and their effects. With the support of renowned scientist Lord Rayleigh, her 1891 paper showed that surface contamination significantly reduces surface tension, and also that changing the characteristics of the surface, compressing or expanding it, also affects surface tension. Decades later, Irving Langmuir and Catharine Blodgett built on Pockle's work in their own trough and important advances in surface chemistry. Langmuir pioneered methods for producing single-molecule layers of film. Blodgett applied these to the development of non-reflective glass, critical for filmmaking and other applications, and also studied methods related to cleaning surfaces, which are important in semiconductor fabrication. The IMFs of attraction between two different molecules are called adhesive forces. Consider what happens when water comes into contact with some surface. If the adhesive forces between water molecules and the molecules of the surface are weak compared to the cohesive forces between the water molecules, the water does not wet the surface. For example, water does not wet waxed surfaces or many plastics such as polyethylene. Water forms drops on these surfaces because the cohesive forces within the drops are greater than the adhesive forces between the water and the plastic. Water spreads out on glass because the adhesive force between water and glass is greater than the cohesive forces within the water. When water is confined in a glass tube, its meniscus surface has a concave shape because the water wets the glass and creeps up the side of the tube. On the other hand, the cohesive forces between mercury atoms are much greater than the adhesive forces between mercury and glass. Mercury therefore does not wet glass, and it forms a convex meniscus when confined in a tube because the cohesive forces within the mercury tend to draw it into a drop. Figure 10.18. This figure shows two test tubes. The test tube on the left contains mercury with a meniscus that rounds up. The test tube on the right contains water with a meniscus that rounds down. Figure 10.18. Differences in the relative strengths of cohesive and adhesive forces result in different meniscus shapes for mercury left and water right in glass tubes. Credit. Mark out if you place one end of a paper towel in spilled wine, as shown in Figure 10.19, the liquid wicks up the paper towel. A similar process occurs in a cloth towel when you use it to dry off after a shower. These are examples of capillary action. When a liquid flows within a porous material due to the attraction of the liquid molecules to the surface of the material and to other liquid molecules, the adhesive forces between the liquid and the porous material, combined with the cohesive forces within the liquid, may be strong enough to move the liquid upward against gravity. A photo and a diagram are shown. In the photo, a paper towel is dipped into a bowl full of a red liquid sitting on a countertop. The red liquid is traveling up the lower part of the paper towel, and this section of the photo has a square drawn around it. A right-facing arrow leads from this square to the image. The image is square and has a background of two types of molecules mixed together. The first type of molecule is composed of two bonded black spheres, one of which is single bonded to three white spheres, and one of which is single bonded to two white spheres, and a red sphere that is itself bonded to a white sphere. The other type of molecule is composed of six black spheres bonded together in a row and bonded to other red and white spheres. Six upward-facing arrows are drawn on top of this background. They have positive signs on their lower ends and negative signs on their heads. Four upward-facing arrows are drawn with their signs reversed. Figure 10.19. Wine wicks up a paper towel, left, because of the strong attractions of water and ethanol molecules to the -O groups on the towel's cellulose fibers, and the strong attractions of water molecules to other water and ethanol molecules, right. Credit photo. Modification of work by Mark Blaser. Towels soak up liquids like water because the fibers of a towel are made of molecules that are attracted to water molecules. Most cloth towels are made of cotton, and paper towels are generally made from paper pulp. Both consist of long molecules of cellulose that contain many -O groups. Water molecules are attracted to these -O groups and form hydrogen bonds with them, which draws the H2O molecules up the cellulose molecules. The water molecules are also attracted to each other, so large amounts of water are drawn up the cellulose fibers. Capillary action can also occur when one end of a small diameter tube is immersed in a liquid, as illustrated in Figure 10. 20. If the liquid molecules are strongly attracted to the tube molecules, the liquid creeps up the inside of the tube until the weight of the liquid and the adhesive forces are in balance. The smaller the diameter of the tube is, the higher the liquid climbs. It is partly by capillary action occurring in plant cells called xylem that water and dissolved nutrients are brought from the soil up through the roots and into a plant. Capillary action is the basis for thin layer chromatography, a laboratory technique commonly used to separate small quantities of mixtures. You depend on a constant supply of tears to keep your eyes lubricated and on capillary action to pump tear fluid away. An image of two beakers and a tube is shown. The first beaker, drawn on the left and labeled water, is drawn half full of a blue liquid. Two open-ended capillary tubes are placed vertically in the beaker and inserted into the liquid. The liquid is shown higher in the tubes than in the beaker and is labeled capillary attraction. The second beaker, drawn in the middle and labeled mercury, is drawn half full of a gray liquid. Two open-ended capillary tubes are placed vertically in the beaker and inserted into the liquid. The liquid is shown lower in the tubes than in the beaker and is labeled capillary repulsion. Lines point to the vertical tubes and label them capillary tubes. A separate drawing of one of the vertical tubes from the first beaker is shown on the right. A right-facing arrow leads from the liquid in the tube to a square call-out box that shows a close-up view of the liquid's surface. The distance across the tube is labeled 2r in this image. Figure 10. 20. Depending upon the relative strengths of adhesive and cohesive forces, a liquid may rise, such as water, or fall, such as mercury, in a glass capillary tube. The extent of the rise, or fall, is directly proportional to the surface tension of the liquid, and inversely proportional to the density of the liquid and the radius of the tube. The height to which a liquid will rise in a capillary tube is determined by several factors as shown in the following equation. Letter 210E equals 2 letter 1D447C, O S letter 1D703, letter 1D45F, letter 1D70C, letter 1D454 in this equation. H is the height of the liquid inside the capillary tube relative to the surface of the liquid outside the tube. T is the surface tension of the liquid. Theta is the contact angle between the liquid and the tube. R is the radius of the tube. Rho is the density of the liquid. And G is the acceleration due to gravity 9. 8ms2. When the tube is made of a material to which the liquid molecules are strongly attracted, they will spread out completely on the surface, which corresponds to a contact angle of 0 degrees. This is the situation for water rising in a glass tube. Example 10. For capillary rise at 25 degrees C, how high will water rise in a glass capillary tube with an inner diameter of 0? 25. For water, T equals 71, 99 mnm, and ρ equals 1 g/cm3. Solution: the liquid will rise to a height h given by letter 210E equals 2 letter 1D447C, O S letter 1D703, letter 1D45F, letter 1D70C, letter 1D454. The Newton is defined as a kg ms2, and so the provided surface tension is equivalent to 0. 7,199 kg/s2. The provided density must be converted into units that will cancel appropriately. Rho equals 1,000 kg/m3. The diameter of the tube in meters is 0. 25 m, so the radius is 0. 125 m for a glass tube immersed in water. The contact angle is theta equals 0 degrees, so cos theta equals 1. Finally, acceleration due to gravity on the Earth is g equals 98 ms2. Substituting these values into the equation and canceling units, we have letter 210E equals 2, 0. 07199 kg/S2 0000125 m 1000 kg/M3 9 8 m/S2 equals 0 12 m equals 12 cm. Check your learning. Water rises in a glass capillary tube to a height of 84 cm. What is the diameter of the capillary tube? Answer: diameter equals 0. 36 Chemistry. In everyday life, biomedical applications of capillary action. Many medical tests require drawing a small amount of blood. For example, to determine the amount of glucose in someone with diabetes or the hematocrit level in an athlete. This procedure can be easily done because of capillary action, the ability of a liquid to flow up a small tube against gravity, as shown in Figure 10. 21. When your finger is pricked, a drop of blood forms and holds together due to surface tension, the unbalanced intermolecular attractions at the surface of the drop. Then, when the open end of a narrow-diameter glass tube touches the drop of blood, the adhesive forces between the molecules in the blood and those at the glass surface draw the blood up the tube. How far the blood goes up the tube depends on the diameter of the tube and the type of fluid. A small tube has a relatively large surface area for a given volume of blood, which results in larger, relative attractive forces, allowing the blood to be drawn farther up the tube. The liquid itself is held together by its own cohesive forces. When the weight of the liquid in the tube generates a downward force equal to the upward force associated with capillary action, the liquid stops rising. A photograph shows a person's hand being held by a person wearing medical gloves. A thin glass tube is pressed against the person's finger and blood is moving up the tube. Figure 10. 21. Blood is collected for medical analysis by capillary action, which draws blood into a small diameter glass tube. Credit: modification of work by Centers for Disease Control and Prevention. Learning objectives. By the end of this section, you will be able to define phase transition and phase transition temperatures, explain the relation between phase transition temperatures and intermolecular attractive forces, describe the processes represented by typical heating and cooling curves, and compute heat flows and enthalpy changes accompanying these processes. We witness and utilize changes of physical state, or phase transitions, in a great number of ways. As one example of global significance, consider the evaporation, condensation, freezing, and melting of water. These changes of state are essential aspects of our Earth's water cycle, as well as many other natural phenomena and technological processes of central importance to our lives. In this module, the essential aspects of phase transitions are explored. Vaporization and condensation. When a liquid vaporizes in a closed container, gas molecules cannot escape. As these gas phase molecules move randomly about, they will occasionally collide with the surface of the condensed phase, and in some cases, these collisions will result in the molecules re-entering the condensed phase. The change from the gas phase to the liquid is called condensation. When the rate of condensation becomes equal to the rate of vaporization, neither the amount of the liquid nor the amount of the vapor in the container changes. The vapor in the container is then said to be in equilibrium with the liquid. Keep in mind that this is not a static situation, as molecules are continually exchanged between the condensed and gaseous phases. Such is an example of a dynamic equilibrium, the status of a system in which reciprocal processes, for example, vaporization and condensation, occur at equal rates. The pressure exerted by the vapor in equilibrium with a liquid in a closed container at a given temperature is called the liquid's vapor pressure, or equilibrium vapor pressure. The area of the surface of the liquid in contact with a vapor and the size of the vessel have no effect on the vapor pressure, although they do affect the time required for the equilibrium to be reached. We can measure the vapor pressure of a liquid by placing a sample in a closed container, like that illustrated in Figure 10. 22. and using a manometer to measure the increase in pressure that is due to the vapor in equilibrium with the condensed phase. 3 images are shown and labeled A, B, and C. Each image shows a round bulb connected on the right to a tube that is horizontal, then is bent vertically, curves, and then is vertical again to make a U-shape. A valve is located in the horizontal portion of the tube. Image A depicts a liquid in the bulb, labeled liquid, and upward-facing arrows leading away from the surface of the liquid. The phrase, "molecules escape surface and form vapor," is written below the bulb, and a gray liquid in the U-shaped portion of the tube is shown at equal heights on the right and left sides. Image B depicts a liquid in the bulb, labeled liquid, and upward-facing arrows leading away from the surface of the liquid to molecules drawn in the upper portion of the bulb. A gray liquid in the U-shaped portion of the tube is shown slightly higher on the right side than on the left side. Image C depicts a liquid in the bulb, labeled liquid, and upward-facing arrows leading away from the surface of the liquid to molecules drawn in the upper portion of the bulb. There are more molecules present in C than in B. The phrase, "equilibrium reached, vapor pressure determined," is written below the bulb, and a gray liquid in the U-shaped portion of the tube is shown higher on the right side. A horizontal line is drawn level with each of these liquid levels, and the distance between the lines is labeled with a double-headed arrow. This section is labeled with the phrase, "vapor pressure." Figure 10.22 In a closed container, dynamic equilibrium is reached when A. The rate of molecules escaping from the liquid to become the gas B increases, and eventually C equals the rate of gas molecules entering the liquid. When this equilibrium is reached, the vapor pressure of the gas is constant, although the vaporization and condensation processes continue. The chemical identities of the molecules in a liquid determine the types and strengths of intermolecular attractions possible. Consequently, different substances will exhibit different equilibrium vapor pressures. Relatively strong intermolecular attractive forces will serve to impede vaporization as well as favoring recapture of gas phase molecules when they collide with the liquid surface, resulting in a relatively low vapor pressure. Weak intermolecular attractions present less of a barrier to vaporization and a reduced likelihood of gas recapture, yielding relatively high vapor pressures. The following example illustrates this dependence of vapor pressure on intermolecular attractive forces. Example 10.5. Explaining vapor pressure in terms of IMFs. Given the shown structural formulas for these 4 compounds, explain their relative vapor pressures in terms of types and extents of IMFs. 4 Lewis structures are shown. The first structure, labeled ethanol, shows a carbon bonded to 3 hydrogen atoms that is single bonded to a second carbon that is bonded to 2 hydrogen atoms and a hydroxyl group. The second structure, labeled ethylene glycol, shows 2 carbon atoms, single bonded to one another, single bonded each to 2 hydrogen atoms, and each single bonded to a hydroxyl group. The third image, labeled diethyl ether, shows an oxygen atom single bonded on both sides to a carbon that is bonded to 2 hydrogens, and a second carbon that is itself bonded to 3 hydrogen atoms. The fourth image, labeled water, shows an oxygen atom that is single bonded on both sides to hydrogen atoms. Solution: diethyl ether has a very small dipole, and most of its intermolecular attractions are London forces. Although this molecule is the largest of the 4 under consideration, its IMFs are the weakest, and as a result, its molecules most readily escape from the liquid. It also has the highest vapor pressure. Due to its smaller size, ethanol exhibits weaker dispersion forces than diethyl ether. However, ethanol is capable of hydrogen bonding and therefore exhibits stronger overall IMFs, which means that fewer molecules escape from the liquid at any given temperature, and so ethanol has a lower vapor pressure than diethyl ether. Water is much smaller than either of the previous substances and exhibits weaker dispersion forces, but its extensive hydrogen bonding provides stronger intermolecular attractions, fewer molecules escaping the liquid, and a lower vapor pressure than for either diethyl ether or ethanol. Ethylene glycol has 2-O groups, so, like water, it exhibits extensive hydrogen bonding. It is much larger than water and thus experiences larger London forces. Its overall IMFs are the largest of these four substances, which means its vaporization rate will be the slowest, and consequently, its vapor pressure the lowest. Check your learning. At 20 degrees C, the vapor pressures of several alcohols are given in this table. Explain these vapor pressures in terms of types and extents of IMFs for these alcohols. Compound methanol CH3OH ethanol CH, 5OH propanol C3H7OH butanol C4H9OH. Vapor pressure at 20 C11, 9 kPa 5, 95 kPa 2, 67 kPa 0, 56 kPa. Answer: all these compounds exhibit hydrogen bonding. These strong IMFs are difficult for the molecules to overcome, so the vapor pressures are relatively low. As the size of molecule increases from methanol to butanol, dispersion forces increase, which means that the vapor pressures decrease as observed. P-methanol, pethanol, P-propanol, P-butanol. As temperature increases, the vapor pressure of a liquid also increases due to the increased average Ke of its molecules. Recall that at any given temperature, the molecules of a substance experience a range of kinetic energies, with a certain fraction of molecules having a sufficient energy to overcome IMF and escape the liquid, vaporize. At a higher temperature, a greater fraction of molecules have enough energy to escape from the liquid, as shown in Figure 10.23. The escape of more molecules per unit of time and the greater average speed of the molecules that escape both contribute to the higher vapor pressure. A graph is shown where the y-axis is labeled number of molecules and the x-axis is labeled kinetic energy. Two lines are graphed and a vertical dotted line, labeled minimum Ke needed to escape, is drawn halfway across the x-axis. The first line moves sharply upward and has a high peak near the left side of the x-axis. It drops just as steeply and ends about 60% of the way across the x-axis. This line is labeled low T. A second line, labeled high T, begins at the same point as the first, but does not go to such a high point, is wider, and ends slightly further to the right on the x-axis. Figure 10.23. Temperature affects the distribution of kinetic energies for the molecules in a liquid. At the higher temperature, more molecules have the necessary kinetic energy, Ke, to escape from the liquid into the gas phase. Boiling points. When the vapor pressure increases enough to equal the external atmospheric pressure, the liquid reaches its boiling point. The boiling point of a liquid is the temperature at which its equilibrium vapor pressure is equal to the pressure exerted on the liquid by its gaseous surroundings. For liquids in open containers, this pressure is due to the Earth's atmosphere. The normal boiling point of a liquid is defined as its boiling point when surrounding pressure is equal to 1 atm, 113 kPa. Figure 10.24 shows the variation in vapor pressure with temperature for several different substances. Considering the definition of boiling point, these curves may be seen as depicting the dependence of a liquid's boiling point on surrounding pressure. A graph is shown where the x-axis is labeled temperature, degree sign, C, and has values of 200 to 1000 in increments of 200, and the y-axis is labeled pressure, Kp, and has values of 20 to 120 in increments of 20. A horizontal dotted line extends across the graph at point 780 on the y-axis, while three vertical dotted lines extend from points 35, 78, and 100 to meet the horizontal dotted line. Four lines are graphed. The first line, labeled ethyl ether, begins at the point 0, 200 and extends in a slight curve to point 45, 1000, while the second line, labeled ethanol, extends from point 020 to point 88, 1000 in a more extreme curve. The third line, labeled water, begins at the point 00 and extends in a curve to point 108, 1000, while the fourth line, labeled ethylene glycol, extends from point 80 to point 140, 100 in a very shallow curve. Figure 10. 24. The boiling points of liquids are the temperatures at which their equilibrium vapor pressures equal the pressure of the surrounding atmosphere. Normal boiling points are those corresponding to a pressure of 1 atm, 101. 3 kPa. Example 10.6. A boiling point at reduced pressure. A typical atmospheric pressure in Leadville, Colorado, elevation 10,200 feet, is 68 kPa. Use the graph in Figure 10. 24 to determine the boiling point of water at this elevation. Solution. The graph of the vapor pressure of water versus temperature in Figure 10. 24 indicates that the vapor pressure of water is 68 kPa at about 90 degrees C. Thus, at about 90 degrees C, the vapor pressure of water will equal the atmospheric pressure in Leadville, and water will boil. Check your learning. The boiling point of ethyl ether was measured to be 10 degrees C at a base camp on the slopes of Mount Everest. Use Figure 10.24 to determine the approximate atmospheric pressure at the camp. Answer: approximately 40 kPa, 04 atm. The quantitative relation between a substance's vapor pressure and its temperature is described by the Clausius-Clapeyron equation. Letter 1d443 equals letter 1d434 letter 1d452 minus delta letter 1d43 bvap slash letter 1d445 letter 1d447, where delta HVAP is the enthalpy of vaporization for the liquid, R is the gas constant, and it is a constant whose value depends on the chemical identity of the substance. Temperature T must be in Kelvin in this equation. This equation is often rearranged into logarithmic form to yield the linear equation. Ln letter 1d443 equals minus delta letter 1d43 bvap letter 1d445 letter 1d447 plus ln letter 1d434. This linear equation may be expressed in a two-point format that is convenient for use in various computations, as demonstrated in the example exercises that follow. If at temperature T1 the vapor pressure is P1, and at temperature T2 the vapor pressure is P2, the corresponding linear equations are ln letter 1d443, 1 equals minus delta letter 1d43 bvap, letter 1d445 letter 1d447, 1 plus ln letter 1d434, a ndln letter 1d443, 2 equals minus delta letter 1d43 bvap, letter 1d445 letter 1d447, 2 plus ln letter 1d434. Since the constant A is the same, these two equations may be rearranged to isolate ln A and then set them equal to one another. ln letter 1d443, 1 plus delta letter 1d43 bvap, letter 1d445 letter 1d447, 1 equals ln letter 1d443, 2 plus delta letter 1d43 bvap, letter 1d445 letter 1d447, 2, which can be combined into ln letter 1d443 to letter 1d443, 1 equals delta letter 1d43 bvap, letter 1d445, 1 letter 1d447, 1 minus 1 letter 1d447, 2. Example 10. 7. Estimating enthalpy of vaporization. Isooctane 2,2,4-trimethylpentane has an octane rating of 100. It is used as one of the standards for the octane rating system for gasoline. At 34 degrees C, the vapor pressure of isooctane is 10 kPa, and at 8 degrees C, its vapor pressure is 100 kPa. Use this information to estimate the enthalpy of vaporization for isooctane. Solution. The enthalpy of vaporization, delta HVAP, can be determined by using the Clausius-Clapeyron equation. Ln, letter 1 d443 to letter 1 d443, 1 equals delta, letter 1 d43 bvap, letter 1 d445, 1 letter 1 d447, 1 minus 1 letter 1 d4472. Since we have two vapor pressure temperature values, T1 equals 34, degrees C equals 307 K, P1 equals 10 kPa, and T2 equals 98. 8 degrees C equals 372. 0 K, P2 equals 100 kPa. We can substitute them into this equation and solve for delta HVAP. Rearranging the Clausius-Clapeyron equation and solving for delta HVAP yields. Delta letter 1 d43 bvap equals letter 1 d445 ln, letter 1 d443 to letter 1 d443 1. 1 letter 1 d447 1 minus 1 letter 1 d447 2 equals 8. 3145 j slash mol k ln 100 k pa 10. 0 k pa 1307. 2 k minus 1372. 0 k equals 33. 800 j slash mol equals 33. 8 kj slash mol. Note that the pressure can be in any units, so long as they agree for both p-values, but the temperature must be in Kelvin for the Clausius-Clapeyron equation to be valid. Check your learning. At 20, 0 degrees C, the vapor pressure of ethanol is 595 kPa, and at 63, 5 degrees C, its vapor pressure is 53.3 kPa. Use this information to estimate the enthalpy of vaporization for ethanol. Answer: 41,360 j/mol or 41.4 kJ/mol. Example 10. 8. Estimating temperature or vapor pressure. For benzene C6H6, the normal boiling point is 80, 1 degrees C, and the enthalpy of vaporization is 30, 8 kJ/mol. What is the boiling point of benzene in Denver, where atmospheric pressure equals 83, 4 kPa? Solution: if the temperature and vapor pressure are known at one point, along with the enthalpy of vaporization, delta HVAP, then the temperature that corresponds to a different vapor pressure, or the vapor pressure that corresponds to a different temperature, can be determined by using the Clausius-Clapeyron equation. Ln, letter 1 d443 to letter 1 d443, 1 equals delta, letter 1 d43 bvap, letter 1 d445, 1 letter 1 d447, 1 minus 1 letter 1 d4472. Since the normal boiling point is the temperature at which the vapor pressure equals atmospheric pressure at sea level, we know one vapor pressure temperature value, T1 equals 80. 1 degrees C equals 353.3 K, P1 equals 101. 3 kPa, delta HVAP equals 38 kJ/mol, and want to find the temperature T2 that corresponds to vapor pressure P2 equals 83. 4 kPa. We can substitute these values into the Clausius-Clapeyron equation and then solve for T2. Rearranging the Clausius-Clapeyron equation and solving for T2 yields. Letter 1 d4472 equals minus letter 1 d445 ln, letter 1 d443 to letter 1 d443 1, delta letter 1 d43 bvap, plus 1 letter 1 d447 1 minus 1 equals minus 8. 3145 j/mol k, ln 83. 4 kPa 101. 3 kPa 30, 800 j/mol plus 1353. 3K minus 1 equals 346, 9K or 73, 8C. Check your learning. For acetone CH3, 2-Co, the normal boiling point is 56, 5 degrees C, and the enthalpy of vaporization is 31, 3 kJ/mol. What is the vapor pressure of acetone at 25, 0 degrees C? Answer: 30. 1 kPa. Enthalpy of vaporization. Vaporization is an endothermic process. The cooling effect can be evident when you leave a swimming pool or a shower. When the water on your skin evaporates, it removes heat from your skin and causes you to feel cold. The energy change associated with the vaporization process is the enthalpy of vaporization, delta H vap. For example, the vaporization of water at standard temperature is represented by H2O, letter 1D459 H2O, letter 1D454 delta, letter 1D43 BVAP equals 44, 1 kJ/mol. As described in the chapter on thermochemistry, the reverse of an endothermic process is exothermic. And so, the condensation of a gas releases heat. H2O, letter 1D454 H2O, letter 1D459, delta letter 1D43 Bcon equals minus delta letter 1D43 BVAP equals minus 44, 0 1 kJ/mol. Example 10.9. Using enthalpy of vaporization. One way our body is cooled is by evaporation of the water in sweat, figure 10.25. In very hot climates, we can lose as much as 1.5 L of sweat per day. Although sweat is not pure water, we can get an approximate value of the amount of heat removed by evaporation by assuming that it is. How much heat is required to evaporate 1.5 L of water, 1.5 kg, at T equals 37 degrees C, normal body temperature. Delta HVAP equals 43, 46 kJ/mol at 37 degrees C. A person's shoulder and neck are shown and their skin is covered in beads of liquid. Figure 10.25. Evaporation of sweat helps cool the body. Credit, Culles/Flicker. Solution. We start with the known volume of sweat, approximated as just water, and use the given information to convert to the amount of heat needed. 1.5 L times 1000 G, 1 L times 1 mol 18 G times 43. 46 kJ 1 mol equals 3. 6 times 103 kJ. Thus, 3600 kJ of heat are removed by the evaporation of 1.5 L of water. Check your learning. How much heat is required to evaporate 100 G of liquid ammonia, NH3, at its boiling point if its enthalpy of vaporization is 48 kJ/mol? Answer: 28 kJ. Melting and freezing. When we heat a crystalline solid, we increase the average energy of its atoms, molecules, or ions, and the solid gets hotter. At some point, the added energy becomes large enough to partially overcome the forces holding the molecules or ions of the solid in their fixed positions, and the solid begins the process of transitioning to the liquid state, or melting. At this point, the temperature of the solid stops rising, despite the continual input of heat, and it remains constant until all of the solid is melted. Only after all of the solid has melted will continued heating increase the temperature of the liquid, figure 10.26. This figure shows 4 photos each labeled A, B, C, and D. Each photo shows a beaker with ice and a digital thermometer. The first photo shows ice cubes in the beaker, and the thermometer reads -12.0 degrees C. The second photo shows slightly melted ice, and the thermometer reads 0 degrees C. The third photo shows more water than ice in the beaker. The thermometer reads 0 degrees C. The fourth photo shows the ice completely melted, and the thermometer reads 22.2 degrees C. Figure 10.26. A. This beaker of ice has a temperature of -12.0 degrees C. B. After 10 minutes, the ice has absorbed enough heat from the air to warm to 0 degrees C. A small amount has melted. C. 30 minutes later, the ice has absorbed more heat, but its temperature is still 0 degrees C. The ice melts without changing its temperature. D. Only after all the ice has melted does the heat absorbed cause the temperature to increase to 22.2 degrees C. Credit. Modification of work by Mark Ott. If we stop heating during melting and place the mixture of solid and liquid in a perfectly insulated container so no heat can enter or escape, the solid and liquid phases remain in equilibrium. This is almost the situation with a mixture of ice and water in a very good thermos bottle. Almost no heat gets in or out, and the mixture of solid ice and liquid water remains for hours. In a mixture of solid and liquid at equilibrium, the reciprocal processes of melting and freezing occur at equal rates, and the quantities of solid and liquid therefore remain constant. The temperature at which the solid and liquid phases of a given substance are in equilibrium is called the melting point of the solid or the freezing point of the liquid. Use of one term or the other is normally dictated by the direction of the phase transition being considered. For example, solid to liquid melting, or liquid to solid freezing. The enthalpy of fusion and the melting point of a crystalline solid depend on the strength of the attractive forces between the units present in the crystal. Molecules with weak attractive forces form crystals with low melting points. Crystals consisting of particles with stronger attractive forces melt at higher temperatures. The amount of heat required to change 1 mole of a substance from the solid state to the liquid state is the enthalpy of fusion, delta H fuss of the substance. The enthalpy of fusion of ice is 60 kJ/mol at 0 degrees C. Fusion, melting, is an endothermic process. H2O, letter 1D460. H2O, letter 1D459 delta letter 1D43B fuss equals 6. 1 kJ/mol. The reciprocal process, freezing, is an exothermic process whose enthalpy change is minus 6. 0 kJ/mol at 0 degrees C. H2O, letter 1D459 H2O. Letter 1D460 delta letter 1D43BFRZ equals minus delta letter 1D43B fuss equals minus 6. 0 1 kJ/mol. Sublimation and deposition. Some solids can transition directly into the gaseous state, bypassing the liquid state via a process known as sublimation. At room temperature and standard pressure, a piece of dry ice, solid CO2, sublimes, appearing to gradually disappear without ever forming any liquid. Snow and ice sublime at temperatures below the melting point of water, a slow process that may be accelerated by winds and the reduced atmospheric pressures at high altitudes. When solid iodine is warmed, the solid sublimes and a vivid purple vapor forms, figure 10.27. The reverse of sublimation is called deposition, a process in which gaseous substances condense directly into the solid state, bypassing the liquid state. The formation of frost is an example of deposition. This figure shows a test tube. In the bottom is a dark substance which breaks up into a purple gas at the top. Figure 10.27. Sublimation of solid iodine in the bottom of the tube produces a purple gas that subsequently deposits as solid iodine on the colder part of the tube above. Credit. Modification of work by Mark Ott. Like vaporization, the process of sublimation requires an input of energy to overcome intermolecular attractions. The enthalpy of sublimation, delta H sub, is the energy required to convert 1 mole of a substance from the solid to the gaseous state. For example, the sublimation of carbon dioxide is represented by CO2, letter 1D460, CO2, letter 1D454, delta letter 1D43B sub equals 26. 1 kJ/mol. Likewise, the enthalpy change for the reverse process of deposition is equal in magnitude but opposite in sign to that for sublimation. CO2, letter 1D454, CO2, letter 1D460, delta letter 1D43B dep equals minus delta letter 1D43B sub equals minus 26. 1 kJ/mol. Consider the extent to which intermolecular attractions must be overcome to achieve a given phase transition. Converting a solid into a liquid requires that these attractions be only partially overcome. Transition to the gaseous state requires that they be completely overcome. As a result, the enthalpy of fusion for a substance is less than its enthalpy of vaporization. This same logic can be used to derive an approximate relation between the enthalpies of all phase changes for a given substance. Though not an entirely accurate description, sublimation may be conveniently modeled as a sequential two-step process of melting, followed by vaporization in order to apply Hess's law. Viewed in this manner, the enthalpy of sublimation for a substance may be estimated as the sum of its enthalpies of fusion and vaporization, as illustrated in Figure 10.28. For example, solid liquid delta, letter 1d43b fus liquid gas delta, letter 1d43b vap, solid gas delta, letter 1d43b sub equals delta letter 1d43b fus plus delta letter 1d43b vap. A diagram is shown with a vertical line drawn on the left side and labeled energy, and three horizontal lines drawn near the bottom, lower third and top of the diagram. These three lines are labeled from bottom to top, solid, liquid, and gas. Near the middle of the diagram, a vertical, upward-facing arrow is drawn from the solid line to the gas line and labeled sublimation, delta sign, H, subscript sub. To the right of this arrow is a second vertical, upward-facing arrow that is drawn from the solid line to the liquid line and labeled fusion, delta sign, H, subscript fus. Above the second arrow is a third arrow drawn from the liquid line to the gas line and labeled vaporization, delta sign, H, subscript vap. Figure 10.28 for a given substance. The sum of its enthalpy of fusion and enthalpy of vaporization is approximately equal to its enthalpy of sublimation. Heating and cooling curves. In the chapter on thermochemistry, the relation between the amount of heat absorbed or released by a substance, Q, and its accompanying temperature change, delta, was introduced. Letter 1d45e equals letter 1d45a letter 1d450, delta, letter 1d447, where m is the mass of the substance and c is its specific heat. The relation applies to matter being heated or cooled, but not undergoing a change in state. When a substance being heated or cooled reaches a temperature corresponding to one of its phase transitions, further gain or loss of heat is a result of diminishing or enhancing intermolecular attractions, instead of increasing or decreasing molecular kinetic energies. While a substance is undergoing a change in state, its temperature remains constant. Figure 10.29 shows a typical heating curve. Consider the example of heating a pot of water to boiling. A stove burner will supply heat at a roughly constant rate. Initially, this heat serves to increase the water's temperature. When the water reaches its boiling point, the temperature remains constant despite the continued input of heat from the stove burner. This same temperature is maintained by the water as long as it is boiling. If the burner setting is increased to provide heat at a greater rate, the water temperature does not rise, but instead the boiling becomes more vigorous, rapid. This behavior is observed for other phase transitions as well. For example, temperature remains constant while the change of state is in progress. A graph is shown where the x-axis is labeled amount of heat added, and the y-axis is labeled temperature, degree sign C, and has values of -10 to 100 in increments of 20. A right-facing horizontal arrow extends from point 0, 0 to the right side of the graph. A line graph begins at the lower left of the graph and moves to point 0 on the y-axis. This segment of the line is labeled H, subscript 2, OS. The line then flattens and travels horizontally for a small distance. This segment is labeled solid begins to melt on its left side and all solid melted on its right side. The line then goes steeply upward in a linear fashion until it hits point 100 on the y-axis. This segment of the line is labeled H, subscript 2, OL. The line then flattens and travels horizontally for a moderate distance. This segment is labeled liquid begins to boil on its left side and all liquid evaporated on its right side. The line then rises to a point above 100 on the y-axis. This segment of the line is labeled H, subscript 2, OG. Figure 10.29. A typical heating curve for a substance depicts changes in temperature that result as the substance absorbs increasing amounts of heat. Plateaus in the curve, regions of constant temperature, are exhibited when the substance undergoes phase transitions. Example 10. Total heat needed to change temperature and phase for a substance. How much heat is required to convert 135 g of ice at -15 degrees C into water vapor at 120 degrees C? Solution. The transition described involves the following steps. Heat ice from -15 C to 0 degrees C. Melt ice. Heat water from 0 C to 100 degrees C. Boil water. Heat steam from 100 degrees C to 120 C. The heat needed to change the temperature of a given substance, with no change in phase, is Q equals M times C times delta. See previous chapter on thermochemistry. The heat needed to induce a given change in phase is given by Q equals N times delta. Using these equations with the appropriate values for specific heat of ice, water, and steam, and enthalpies of fusion and vaporization, we have letter 1 D45E total equals letter 1 D45A, letter 1 D450 delta, letter 1 D447 ice, plus letter 1 D45B delta, letter 1 D43B fuss, plus letter 1 D45A, letter 1 D450 delta, letter 1 D447. Water plus letter 1 D45B delta, letter 1 D43B vap plus letter 1 D45A, letter 1 D450 delta, letter 1 D447 steam equals 135 G2. 9J/G degrees C 15 degrees C plus 135 G1 mol 18. 02 G6. 1 kJ/mol plus 135 G4. 18J/G degrees C 100 degrees C plus 135 G1 mol 18. 02 G40. 67 kJ/mol plus 135 G1. 86J/G degrees C 20 degrees C equals 4,230 J plus 45. 0 kJ plus 56500 J plus 305 kJ plus 5022 J. Converting the quantities in J to kJ permits them to be summed, yielding the total heat required. Equals 4. 23 kJ plus 45, 0 kJ plus 56, 5 kJ plus 305 kJ plus 5, 2 kJ equals 416 kJ. Note, the value of delta HVAP at the boiling point of water, 4067 kJ/mol, is used here instead of the value at standard temperature, 44. 1 kJ/mol. Check your learning. What is the total amount of heat released when 94 G water at 80, 0 degrees C cools to form ice at -30, 0 degrees C? Answer, 68.7 kJ. Learning objectives. By the end of this section, you will be able to explain the construction and use of a typical phase diagram. Use phase diagrams to identify stable phases at given temperatures and pressures, and to describe phase transitions resulting from changes in these properties. Describe the supercritical fluid phase of matter. In the previous module, the variation of a liquid's equilibrium vapor pressure with temperature was described. Considering the definition of boiling point, plots of vapor pressure versus temperature represent how the boiling point of the liquid varies with pressure. Also described was the use of heating and cooling curves to determine a substance's melting or freezing point. Making such measurements over a wide range of pressures yields data that may be presented graphically as a phase diagram. A phase diagram combines plots of pressure versus temperature for the liquid-gas, solid-liquid, and solid-gas phase transition equilibria of a substance. These diagrams indicate the physical states that exist under specific conditions of pressure and temperature, and also provide the pressure dependence of the phase transition temperatures, melting points, sublimation points, boiling points. A typical phase diagram for a pure substance is shown in Figure 10. 30. A graph is shown where the x-axis is labeled temperature and the y-axis is labeled pressure. A line extends from the lower left bottom of the graph sharply upward to a point that is a third across the x-axis. A second line begins at the lower third of the first line at a point labeled triple point and extends to the upper right corner of the graph where it is labeled critical point. The two lines bisect the graph area to create three sections, labeled solid near the top left, liquid in the top middle, and gas near the bottom right. A pair of horizontal arrows, one left-facing and labeled deposition, and one right-facing and labeled sublimation, are drawn on top of the bottom section of the first line. A second pair of horizontal arrows, one left-facing and labeled freezing, and one right-facing and labeled melting, are drawn on top of the upper section of the first line. A third pair of horizontal arrows, one left-facing and labeled condensation, and one right-facing and labeled vaporization, are drawn on top of the middle section of the second line. Figure 10. 30. The physical state of a substance and its phase transition temperatures are represented graphically in a phase diagram. To illustrate the utility of these plots, consider the phase diagram for water shown in Figure 10. 31. A graph is shown where the x-axis is labeled temperature in degrees Celsius, and the y-axis is labeled pressure, Kp. A line extends from the origin of the graph, which is labeled A, sharply upward to a point in the bottom third of the diagram labeled B, where it branches into a line that slants slightly backward until it hits the highest point on the y-axis labeled D, and a second line that extends to the upper right corner of the graph labeled C. C is labeled critical point, with a dotted line extending downward to the x-axis labeled 374 degrees Celsius, and another dotted line extending to the y-axis labeled 22,089 kPa. The two lines bisect the graph area to create three sections, labeled ice solid near the middle left, water liquid in the top middle, and water vapor gas near the bottom middle. Point B is labeled triple point and has a dotted line extending downward to the x-axis labeled 0, 1, and another dotted line extending to the y-axis labeled 0, 6. Halfway between points B and C, a dotted line extends from the originally discussed line downward to the point 100 degrees Celsius on the x-axis, and another dotted line extends to the y-axis at 101 kPa. Another dotted line extends from this dotted line downward at 0 degrees Celsius. Figure 10. 31. The pressure and temperature axes on this phase diagram of water are not drawn to constant scale in order to illustrate several important properties. We can use the phase diagram to identify the physical state of a sample of water under specified conditions of pressure and temperature. For example, a pressure of 50 kPa and a temperature of -10 degrees C correspond to the region of the diagram labeled ice. Under these conditions, water exists only as a solid ice. A pressure of 50 kPa and a temperature of 50 degrees C correspond to the water region. Here, water exists only as a liquid. At 25 kPa and 200 degrees C, water exists only in the gaseous state. Note that on the H2O phase diagram, the pressure and temperature axes are not drawn to a constant scale in order to permit the illustration of several important features as described here. The curve BC in Figure 10. 31 is the plot of vapor pressure versus temperature as described in the previous module of this chapter. This liquid-vapor curve separates the liquid and gaseous regions of the phase diagram and provides the boiling point for water at any pressure. For example, at 1 atm, the boiling point is 100 degrees C. Notice that the liquid-vapor curve terminates at a temperature of 374 degrees C and a pressure of 218 atm, indicating that water cannot exist as a liquid above this temperature, regardless of the pressure. The physical properties of water under these conditions are intermediate between those of its liquid and gaseous phases. This unique state of matter is called a supercritical fluid, a topic that will be described in the next section of this module. The solid vapor curve, labeled OB in Figure 1031, indicates the temperatures and pressures at which ice and water vapor are in equilibrium. These temperature-pressure data pairs correspond to the sublimation, or deposition, points for water. If we could zoom in on the solid gas line in Figure 1031, we would see that ice has a vapor pressure of about 0.20 kPa at minus 10 degrees C. Thus, if we place a frozen sample in a vacuum with a pressure less than 0.20 kPa, ice will sublime. This is the basis for the freeze-drying process often used to preserve foods, such as the ice cream shown in Figure 1032. A photograph shows a package with a rocket being launched on the front and a block of pink, white, and brown striped solid in a wrapper next to it. Figure 1032. Freeze-dried foods like this ice cream are dehydrated by sublimation at pressures below the triple point for water. Credit: letter 2BA, LW, letter 2BA/flicker. The solid-liquid curve, labeled BD, shows the temperatures and pressures at which ice and liquid water are in equilibrium, representing the melting freezing points for water. Note that this curve exhibits a slight negative slope, greatly exaggerated for clarity, indicating that the melting point for water decreases slightly as pressure increases. Water is an unusual substance in this regard, as most substances exhibit an increase in melting point with increasing pressure. This behavior is partly responsible for the movement of glaciers, like the one shown in Figure 1033. The bottom of a glacier experiences an immense pressure due to its weight that can melt some of the ice, forming a layer of liquid water on which the glacier may more easily slide. A photograph shows an aerial view of a land mass. The white mass of a glacier is shown near the top left quadrant of the photo and leads to two branching blue rivers. The open land is shown in brown. Figure 1033. The immense pressures beneath glaciers result in partial melting to produce a layer of water that provides lubrication to assist glacial movement. This satellite photograph shows the advancing edge of the Perito Moreno Glacier in Argentina. Credit: NASA. The point of intersection of all three curves is labeled B in Figure 1031. At the pressure and temperature represented by this point, three phases of water coexist in equilibrium. This temperature-pressure data pair is called the triple point. At pressures lower than the triple point, water cannot exist as a liquid regardless of the temperature. Example 10.11. Determining the state of water. Using the phase diagram for water given in Figure 1031, determine the state of water at the following temperatures and pressures: A minus 10 degrees C and 50 kPa. B 25 degrees C and 90 kPa. C 50 degrees C and 40 kPa. D 80 degrees C and 5 kPa. E minus 10 degrees C and 0.3 kPa. F 50 degrees C and 0.3 kPa. Solution: using the phase diagram for water, we can determine that the state of water at each temperature and pressure given are as follows: A solid, B liquid, C liquid, D gas, E solid, F gas. Check your learning. What phase changes can water undergo as the temperature changes if the pressure is held at 0.3 kPa? If the pressure is held at 50 kPa? Answer: at 0.3 kPa, Sg. At minus 58 degrees C, at 50 kPa, Sl. At 0 degrees C, Lg. At 78 C. Consider the phase diagram for carbon dioxide shown in Figure 1034 as another example. The solid-liquid curve exhibits a positive slope, indicating that the melting point for CO2 increases with pressure as it does for most substances, water being a notable exception as described previously. Notice that the triple point is well above 1 atm, indicating that carbon dioxide cannot exist as a liquid under ambient pressure conditions. Instead, Cooling gaseous carbon dioxide at 1 atm results in its deposition into the solid state. Likewise, solid carbon dioxide does not melt at 1 atm pressure, but instead sublimes to yield gaseous CO2. Finally, notice that the critical point for carbon dioxide is observed at a relatively modest temperature and pressure in comparison to water. A graph is shown where the x-axis is labeled temperature, degree sign, C, and has values of -100 to 100 in increments of 25, and the y-axis is labeled pressure, Kp, and has values of 10 to 1 million. A line extends from the lower left bottom of the graph upward to a point around 27,9,000, where it ends. The space under this curve is labeled gas. A second line extends in a curve from point around -55,500 to 27, 1 million. The area to the left of this line and above the first line is labeled solid, while the area to the right is labeled liquid. A section on the graph under the second line and past the point 28 on the x-axis is labeled SCF. Figure 10:34 a phase diagram for carbon dioxide is shown. The pressure axis is plotted on a logarithmic scale to accommodate the large range of values. Example 10.12. Determining the state of carbon dioxide. Using the phase diagram for carbon dioxide shown in Figure 10.34, determine the state of CO2 at the following temperatures and pressures: A -30 degrees C and 2000 kPa, B -90 degrees C and 1000 kPa, C -60 degrees C and 100 kPa, D -40 C and 1500 kPa, E 0 degrees C and 100 kPa, F 20 degrees C and 100 kPa. Solution. Using the phase diagram for carbon dioxide provided, we can determine that the state of CO2 at each temperature and pressure given are as follows: A liquid, B solid, C gas, D liquid, E gas, F gas. Check your learning. Identify the phase changes that carbon dioxide will undergo as its temperature is increased from -100 C, while holding its pressure constant at 1500 kPa. At 50 kPa, at what approximate temperatures do these phase changes occur? Answer: at 1500 kPa, SL. At -55 degrees C, LG. At -10 degrees C, at 50 kPa, SG. At -60 degrees C. Supercritical fluids. If we place a sample of water in a sealed container at 25 degrees C, remove the air, and let the vaporization-condensation equilibrium establish itself, we are left with a mixture of liquid water and water vapor at a pressure of 0.3 atm. A distinct boundary between the more dense liquid and the less dense gas is clearly observed. As we increase the temperature, the pressure of the water vapor increases, as described by the liquid gas curve in the phase diagram for water, Figure 10.31, and a two-phase equilibrium of liquid and gaseous phases remains. At a temperature of 374 degrees C, the vapor pressure has risen to 218 atm, and any further increase in temperature results in the disappearance of the boundary between liquid and vapor phases. All of the water in the container is now present in a single phase whose physical properties are intermediate between those of the gaseous and liquid states. This phase of matter is called a supercritical fluid, and the temperature and pressure above which this phase exists is the critical point, Figure 10.35. Above its critical temperature, a gas cannot be liquefied no matter how much pressure is applied. The pressure required to liquefy a gas at its critical temperature is called the critical pressure. The critical temperatures and critical pressures of some common substances are given in the following table. Substance critical temperature, degrees C, critical pressure, kPa. Hydrogen -240, 1,300. Nitrogen -147, 3,400. Oxygen -118, 5,000. Carbon dioxide 31, 17,400. Ammonia 132, 411 300. Sulfur dioxide 157, 7,800. Water 374, 22,000. Four photographs are shown where each shows a circular container with a green and red float in each. In the left diagram, the container is half filled with a colorless liquid, and the floats sit on the surface of the liquid. In the second photo, the green float is near the top, and the red float lies near the bottom of the container. In the third photo, the fluid is darker and the green float sits halfway up the container, while the red is sitting at the bottom. In the right photo, the liquid is colorless again and the two floats sit on the surface. Figure 10. 35A. A sealed container of liquid carbon dioxide slightly below its critical point is heated, resulting in B, the formation of the supercritical fluid phase. Cooling the supercritical fluid lowers its temperature and pressure below the critical point, resulting in the reestablishment of separate liquid and gaseous phases, C and D. Colored floats illustrate differences in density between the liquid, gaseous, and supercritical fluid states. Credit: Modification of work by MRM Robin/YouTube. Link to learning. Observe the liquid to supercritical fluid transition for carbon dioxide. Like a gas, a supercritical fluid will expand and fill a container, but its density is much greater than typical gas densities, typically being close to those for liquids. Similar to liquids, these fluids are capable of dissolving non-volatile solutes. They exhibit essentially no surface tension and very low viscosities, however, so they can more effectively penetrate very small openings in a solid mixture and remove soluble components. These properties make supercritical fluids extremely useful solvents for a wide range of applications. For example, supercritical carbon dioxide has become a very popular solvent in the food industry, being used to decaffeinate coffee, remove fats from potato chips, and extract flavor and fragrance compounds from citrus oils. It is non-toxic, relatively inexpensive, and not considered to be a pollutant. After use, the CO2 can be easily recovered by reducing the pressure and collecting the resulting gas. Example 10. 13. The critical temperature of carbon dioxide. If we shake a carbon dioxide fire extinguisher on a cool day, 18 degrees C, we can hear liquid CO2 sloshing around inside the cylinder. However, the same cylinder appears to contain no liquid on a hot summer day, 35 degrees C. Explain these observations. Solution: on the cool day, the temperature of the CO2 is below the critical temperature of CO2, 304 K or 31 degrees C, so liquid CO2 is present in the cylinder. On the hot day, the temperature of the CO2 is greater than its critical temperature of 31 degrees C. Above this temperature, no amount of pressure can liquefy CO2, so no liquid CO2 exists in the fire extinguisher. Check your learning. Ammonia can be liquefied by compression at room temperature. Oxygen cannot be liquefied under these conditions. Why do the two gases exhibit different behavior? Answer: the critical temperature of ammonia is 405 K, which is higher than room temperature. The critical temperature of oxygen is below room temperature, thus oxygen cannot be liquefied at room temperature. Chemistry in everyday life. Decaffeinating coffee using supercritical CO2. Coffee is the world's second most widely traded commodity, following only petroleum. Across the globe, people love coffee's aroma and taste. Many of us also depend on one component of coffee, caffeine, to help us get going in the morning or stay alert in the afternoon. But late in the day, coffee's stimulant effect can keep you from sleeping, so you may choose to drink decaffeinated coffee in the evening. Since the early 1900s, many methods have been used to decaffeinate coffee. All have advantages and disadvantages, and all depend on the physical and chemical properties of caffeine. Because caffeine is a somewhat polar molecule, it dissolves well in water, a polar liquid. However, Since many of the other 400+ compounds that contribute to coffee's taste and aroma also dissolve in H2O, hot water decaffeination processes can also remove some of these compounds, adversely affecting the smell and taste of the decaffeinated coffee. Dichloromethane, CH2Cl2, and ethyl acetate, CH3-CoAcetyl-5, have similar polarity to caffeine and are therefore very effective solvents for caffeine extraction, but both also remove some flavor and aroma components, and their use requires long extraction and cleanup times. Because both of these solvents are toxic, health concerns have been raised regarding the effect of residual solvent remaining in the decaffeinated coffee. Supercritical fluid extraction using carbon dioxide is now being widely used as a more effective and environmentally friendly decaffeination method. Figure 10. 36. At temperatures above 304, 2K and pressures above 73-76 kPa, CO2 is a supercritical fluid with properties of both gas and liquid. Like a gas, it penetrates deep into the coffee beans. Like a liquid, it effectively dissolves certain substances. Supercritical carbon dioxide extraction of steamed coffee beans removes 97–99% of the caffeine, leaving coffee's flavor and aroma compounds intact. Because CO2 is a gas under standard conditions, its removal from the extracted coffee beans is easily accomplished, as is the recovery of the caffeine from the extract. The caffeine recovered from coffee beans via this process is a valuable product that can be used subsequently as an additive to other foods or drugs. Two images are shown and labeled A and B. Image A shows a molecule composed of a 5-member ring composed of 2 blue spheres and 3 black spheres. One of the blue spheres is bonded to a black sphere, bonded to 3 white spheres, and one of the black spheres is bonded to a white sphere. The other 2 black spheres are double bonded together and make up one side of a 6-membered ring that is also composed of 2 more black spheres and 2 blue spheres, both of which are bonded to a black sphere bonded to 3 white spheres. The black spheres are each double bonded to red spheres. Image B shows a diagram of 2 vertical tubes that lie next to one another. The left-hand tube is labeled extraction vessel. A small tube labeled soaked beans leads into the top of the tube, and a label at the bottom of the tube reads decaffeinated beans. The right tube is labeled absorption vessel. A tube near the top of this tube is labeled water, and another tube leads from the right tube to the left. This tube is labeled with a left-facing arrow and the phrase supercritical carbon dioxide. There is a tube leading away from the bottom which is labeled caffeine and water. There is another tube that leads from the extraction vessel to the absorption vessel which is labeled supercritical CO subscript 2 plus caffeine. Figure 10. 36a. Caffeine molecules have both polar and nonpolar regions, making it soluble in solvents of varying polarities. B. The schematic shows a typical decaffeination process involving supercritical carbon dioxide. Learning objectives. By the end of this section, you will be able to define and describe the bonding and properties of ionic, molecular, metallic, and covalent network crystalline solids. Describe the main types of crystalline solids: ionic solids, metallic solids, covalent network solids, and molecular solids. Explain the ways in which crystal defects can occur in a solid. When most liquids are cooled, they eventually freeze and form crystalline solids, solids in which the atoms, ions, or molecules are arranged in a definite repeating pattern. It is also possible for a liquid to freeze before its molecules become arranged in an orderly pattern. The resulting materials are called amorphous solids or non-crystalline solids, or sometimes glasses. The particles of such solids lack an ordered internal structure and are randomly arranged. Figure 10. 37. 2 images are shown and labeled from left to right, crystalline and amorphous. The crystalline diagram shows many circles drawn in rows and stacked together tightly. The amorphous diagram shows many circles spread slightly apart and in no organized pattern. Figure 10. 37. The entities of a solid phase may be arranged in a regular, repeating pattern crystalline solids or randomly amorphous. Metals and ionic compounds typically form ordered crystalline solids. Substances that consist of large molecules, or a mixture of molecules whose movements are more restricted, often form amorphous solids. For examples, candle waxes are amorphous solids composed of large hydrocarbon molecules. Some substances, such as silicon dioxide, shown in Figure 10. 38, can form either crystalline or amorphous solids, depending on the conditions under which it is produced. Also, amorphous solids may undergo a transition to the crystalline state under appropriate conditions. Two sets of molecules are shown. The first set of molecules contains 5 identical, hexagonal rings composed of alternating red and maroon spheres single-bonded together, and with a red spheres extending outward from each maroon sphere. The second set of molecules shows 4 rings with 12 sides each that are joined together. Each ring is composed of alternating red and maroon spheres single-bonded together, and with a red spheres extending outward from each maroon sphere. Figure 10. 38a. Silicon dioxide, CO2, is abundant in nature as one of several crystalline forms of the mineral quartz. B. Rapid cooling of molten CO2 yields an amorphous solid known as fused silica. Crystalline solids are generally classified according to the nature of the forces that hold its particles together. These forces are primarily responsible for the physical properties exhibited by the bulk solids. The following sections provide descriptions of the major types of crystalline solids: ionic, metallic, covalent network, and molecular. Ionic solids. Ionic solids, such as sodium chloride and nickel oxide, are composed of positive and negative ions that are held together by electrostatic attractions, which can be quite strong. Figure 10. 39. Many ionic crystals also have high melting points. This is due to the very strong attractions between the ions. In ionic compounds, the attractions between full charges are much larger than those between the partial charges in polar molecular compounds. This will be looked at in more detail in a later discussion of lattice energies. Although they are hard, they also tend to be brittle, and they shatter rather than bend. Ionic solids do not conduct electricity. However, they do conduct when molten or dissolved because their ions are free to move. Many simple compounds formed by the reaction of a metallic element with a non-metallic element are ionic. This figure shows large purple spheres bonded to smaller green spheres in an alternating pattern. The spheres are arranged in a cube. Figure 10. 39. Sodium chloride is an ionic solid. Metallic solids. Metallic solids such as crystals of copper, aluminum, and iron are formed by metal atoms. Figure 10. 40. The structure of metallic crystals is often described as a uniform distribution of atomic nuclei within a sea of delocalized electrons. The atoms within such a metallic solid are held together by a unique force known as metallic bonding that gives rise to many useful and varied bulk properties. All exhibit high thermal and electrical conductivity, metallic luster, and malleability. Many are very hard and quite strong. Because of their malleability, the ability to deform under pressure or hammering, they do not shatter and therefore make useful construction materials. The melting points of the metals vary widely. Mercury is a liquid at room temperature, and the alkali metals melt below 200 degrees C. Several post-transition metals also have low melting points, whereas the transition metals melt at temperatures above 1000 degrees C. These differences reflect differences in strengths of metallic bonding among the metals. This figure shows large brown spheres arranged in a cube. Figure 10. 40. Copper is a metallic solid. Covalent network solid. Covalent network solids include crystals of diamond, silicon, some other nonmetals, and some covalent compounds such as silicon dioxide, sand, and silicon carbide, carborundum, the abrasive on sandpaper. Many minerals have networks of covalent bonds. The atoms in these solids are held together by a network of covalent bonds, as shown in Figure 10.41. To break or to melt a covalent network solid, covalent bonds must be broken. Because covalent bonds are relatively strong, covalent network solids are typically characterized by hardness, strength, and high melting points. For example, diamond is one of the hardest substances known and melts above 3,500 degrees C. Four pairs of images are shown. In the first pair, a square box containing a black atom bonded to four other black atoms is shown above a structure composed of many black atoms, each bonded to four other black atoms, where one of the upper atoms is labeled carbon, and the whole structure is labeled diamond. In the second pair, a square box containing a white atom bonded to four red atoms is shown above a structure composed of many white atoms, each bonded to four red atoms, where one of the red atoms is labeled oxygen, and one of the white atoms is labeled silicon. The whole structure is labeled silicon dioxide. In the third pair, a square box containing a blue atom bonded to four white atoms is shown above a structure composed of many blue atoms, each bonded to four white atoms, where one of the blue atoms is labeled carbon, and one of the white atoms is labeled silicon. The whole structure is labeled silicon carbide. In the fourth pair, a square box containing six black atoms bonded into a ring is shown above a structure composed of many rings, arranged into sheets layered one atop the other, where one of the black atoms is labeled carbon. The whole structure is labeled graphite. Figure 10.41. A covalent crystal contains a three-dimensional network of covalent bonds, as illustrated by the structures of diamond, silicon dioxide, silicon carbide, and graphite. Graphite is an exceptional example, composed of planar sheets of covalent crystals that are held together in layers by non-covalent forces. Unlike typical covalent solids, graphite is very soft and electrically conductive. Molecular solid. Molecular solids such as ice, sucrose, table sugar, and iodine, as shown in Figure 10.42, are composed of neutral molecules. The strengths of the attractive forces between the units present in different crystals vary widely, as indicated by the melting points of the crystals. Small symmetrical molecules, nonpolar molecules, such as H2, N2, O2, and F2, have weak attractive forces and form molecular solids with very low melting points, below -200 degrees C. Substances consisting of larger, nonpolar molecules have larger attractive forces and melt at higher temperatures. Molecular solids composed of molecules with permanent dipole moments, polar molecules, melt at still higher temperatures. Examples include ice melting point 0 degrees C and table sugar melting point 185 degrees C. Two images are shown and labeled carbon dioxide and iodine. The carbon dioxide structure is composed of molecules, each made up of one gray and two red atoms, stacked together into a cube. The image of iodine shows pairs of purple atoms arranged near one another, but not touching. Figure 10.42. Carbon dioxide, Co2, consists of small, nonpolar molecules and forms a molecular solid with a melting point of -78 degrees C. Iodine, I2, consists of larger, nonpolar molecules and forms a molecular solid that melts at 114 degrees C. Properties of solids. A crystalline solid, like those listed in Table 10.4, has a precise melting temperature because each atom or molecule of the same type is held in place with the same forces or energy. Thus, the attractions between the units that make up the crystal all have the same strength and all require the same amount of energy to be broken. The gradual softening of an amorphous material differs dramatically from the distinct melting of a crystalline solid. This results from the structural non-equivalence of the molecules in the amorphous solid. Some forces are weaker than others, and when an amorphous material is heated, the weakest intermolecular attractions break first. As the temperature is increased further, the stronger attractions are broken. Thus, amorphous materials soften over a range of temperatures. Types of crystalline solids and their properties. Type of solid, type of particles, type of attractions, properties, examples. Ionic ions, ionic bonds, hard, brittle, conducts electricity as a liquid but not as a solid. High to very high melting points, NaCl, Al2O3. Metallic atoms of electropositive elements, metallic bonds, shiny, malleable, ductile, conducts heat and electricity well. Variable hardness and melting temperature, Q, Phi. TPB-U. Covalent network atoms of electronegative elements, covalent bonds, very hard, not conductive, very high melting point, C, diamond, CO2. CC. Molecular molecules or atoms, IMPs, variable hardness, variable brittleness, not conductive, low melting points, H2O, CO2, I2, C12H22O11. Table 10. 4. How sciences interconnect. Graphene, material of the future. Carbon is an essential element in our world. The unique properties of carbon atoms allow the existence of carbon-based life forms such as ourselves. Carbon forms a huge variety of substances that we use on a daily basis, including those shown in Figure 10. 43. You may be familiar with diamond and graphite, the two most common allotropes of carbon. Allotropes are different structural forms of the same element. Diamond is one of the hardest known substances, whereas graphite is soft enough to be used as pencil lead. These very different properties stem from the different arrangements of the carbon atoms in the different allotropes. 3 pairs of images are shown, each composed of a photo and a diagram. In the first pair, the photo shows a close-up view of a colorless, multifaceted crystal, and the diagram shows many gray spheres bonded together in a net-like structure. The caption below this pair reads diamond. In the second pair, the photo shows a rough textured dark gray solid, while the image shows 4 horizontal sheets, composed of interlocking black spheres, lying atop one another. This pair has a caption that reads graphite. The third pair shows a photo of 12 black hexagons on a yellow background where 2 of the hexagons are encircled by a gray border, and a caption of 14 times 10, superscript -10, m, distance between center of atoms, and an image of many black hexagons evenly arranged on a yellow background. The caption below this pair of images reads, graphite surface. Figure 10. 43. Diamond is extremely hard because of the strong bonding between carbon atoms in all directions. Graphite in pencil lead rubs off onto paper due to the weak attractions between the carbon layers. An image of a graphite surface shows the distance between the centers of adjacent carbon atoms. Credit left photo. Modification of work by Steve Jurvetson. Credit middle photo. Modification of work by United States Geological Survey. You may be less familiar with a recently discovered form of carbon, graphene. Graphene was first isolated in 2004 by using tape to peel off thinner and thinner layers from graphite. It is essentially a single sheet, 1 atom thick of graphite. Graphene, illustrated in Figure 10. 44, is not only strong and lightweight, but it is also an excellent conductor of electricity and heat. These properties may prove very useful in a wide range of applications, such as vastly improved computer chips and circuits, better batteries and solar cells, and stronger and lighter structural materials. The 2010 Nobel Prize in Physics was awarded to Andrei Geim and Konstantin Novoselov for their pioneering work with graphene. 4 images are shown. In the upper image, labeled graphene sheet, a box is drawn around a sheet of interconnected hexagonal rings. In the lower left image, a sphere is composed of hexagonal rings linked together and is labeled buckyball. In the lower middle image, A tube is shown that is composed of many hexagonal rings joined together and is labeled nanotube. In the lower right image, 4 horizontal sheets composed of joined hexagonal rings is shown and labeled stacked sheets. Figure 10. 44 graphene sheets can be formed into buckyballs, nanotubes, and stacked layers. Crystal defects. In a crystalline solid, the atoms, ions, or molecules are arranged in a definite repeating pattern, but occasional defects may occur in the pattern. Several types of defects are known, as illustrated in Figure 10. 45. Vacancies are defects that occur when positions that should contain atoms or ions are vacant. Less commonly, some atoms or ions in a crystal may occupy positions, called interstitial sites, located between the regular positions for atoms. Other distortions are found in impure crystals, as, for example, when the cations, anions, or molecules of the impurity are too large to fit into the regular positions without distorting the structure. Trace amounts of impurities are sometimes added to a crystal, a process known as doping, in order to create defects in the structure that yield desirable changes in its properties. For example, silicon crystals are doped with varying amounts of different elements to yield suitable electrical properties for their use in the manufacture of semiconductors and computer chips. A diagram is shown in which 144 spheres are arranged in a 12 by 12 square. A gap in the square is labeled vacancy, while one sphere that is a different color from all the rest is labeled interstitial impurity. The top right corner of the square is disturbed and has a larger sphere inserted that is labeled substitution impurity atom. Figure 10. 45 types of crystal defects include vacancies, interstitial atoms, and substitutions impurities. Learning objectives. By the end of this section, you will be able to describe the arrangement of atoms and ions in crystalline structures, compute ionic radii using unit cell dimensions, explain the use of X-ray diffraction measurements in determining crystalline structures. Over 90% of naturally occurring and man-made solids are crystalline. Most solids form with a regular arrangement of their particles because the overall attractive interactions between particles are maximized, and the total intermolecular energy is minimized when the particles pack in the most efficient manner. The regular arrangement at an atomic level is often reflected at a macroscopic level. In this module, we will explore some of the details about the structures of metallic and ionic crystalline solids and learn how these structures are determined experimentally. The structures of metals. We will begin our discussion of crystalline solids by considering elemental metals, which are relatively simple because each contains only one type of atom. A pure metal is a crystalline solid with metal atoms packed closely together in a repeating pattern. Some of the properties of metals in general, such as their malleability and ductility, are largely due to having identical atoms arranged in a regular pattern. The different properties of one metal compared to another partially depend on the sizes of their atoms and the specifics of their spatial arrangements. We will explore the similarities and differences of 4 of the most common metal crystal geometries in the sections that follow. Unit cells of metals. The structure of a crystalline solid, whether a metal or not, is best described by considering its simplest repeating unit, which is referred to as its unit cell. The unit cell consists of lattice points that represent the locations of atoms or ions. The entire structure, then, consists of this unit cell repeating in 3 dimensions, as illustrated in Figure 10. 46. A diagram of 2 images is shown. In the first image, a cube with a sphere at each corner is shown. The cube is labeled unit cell, and the spheres at the corners are labeled lattice points. The second image shows the same cube, but this time it is one cube amongst 8 that make up a larger cube. The original cube is shaded a color while the other cubes are not. Figure 10. 46. A unit cell shows the locations of lattice points repeating in all directions. Let us begin our investigation of crystal lattice structure and unit cells with the most straightforward structure and the most basic unit cell. To visualize this, imagine taking a large number of identical spheres, such as tennis balls, and arranging them uniformly in a container. The simplest way to do this would be to make layers in which the spheres in one layer are directly above those in the layer below, as illustrated in Figure 10.47. This arrangement is called simple cubic structure, and the unit cell is called the simple cubic unit cell or primitive cubic unit cell. A diagram of three images is shown. In the first image, a cube with a sphere at each corner is shown. The spheres at the corners are circled. The second image shows the same cube, but this time the spheres at the corners are larger and shaded in. In the third image, the cube is one cube amongst 8 that make up a larger cube. The original cube is shaded a color while the other cubes are not. Figure 10.47. When metal atoms are arranged with spheres in one layer directly above or below spheres in another layer, the lattice structure is called simple cubic. Note that the spheres are in contact. In a simple cubic structure, the spheres are not packed as closely as they could be, and they only fill about 52% of the volume of the container. This is a relatively inefficient arrangement, and only one metal, polonium, Po, crystallizes in a simple cubic structure. As shown in Figure 10.48, a solid with this type of arrangement consists of planes or layers, in which each atom contacts only the 4 nearest neighbors in its layer. One atom directly above it in the layer above, and one atom directly below it in the layer below. The number of other particles that each particle in a crystalline solid contacts is known as its coordination number. For a polonium atom in a simple cubic array, the coordination number is therefore 6. A diagram of two images is shown. In the first image, 8 stacked cubes that make up one large cube are shown. 3 lines that run from top to bottom, front to back, and sided to side in the middle of the structure are shaded darker than the rest of the lines. The second image shows the same set of cubes, but this time spheres at the end of each line are numbered. The horizontal line that goes left to right is labeled with a 2 and a 5. The vertical line is labeled with a 1 and a 6. And the line that goes horizontally front to back is labeled with a 3 and a 4. Figure 10.48. An atom in a simple cubic lattice structure contacts 6 other atoms, so it has a coordination number of 6. In a simple cubic lattice, the unit cell that repeats in all directions is a cube defined by the centers of 8 atoms, as shown in Figure 10.49. Atoms at adjacent corners of this unit cell contact each other, so the edge length of this cell is equal to 2 atomic radii, or 1 atomic diameter. A cubic unit cell contains only the parts of these atoms that are within it. Since an atom at a corner of a simple cubic unit cell is contained by a total of 8 unit cells, only 1/8 of that atom is within a specific unit cell. And since each simple cubic unit cell has one atom at each of its 8 corners, there is 8 times 18 equals 1 atom within one simple cubic unit cell. A diagram of two images is shown. In the first image, 8 spheres are stacked together to form a cube, and dots at the center of each sphere are connected to form a cube shape. The dots are labeled lattice points, while a label under the image reads simple cubic lattice cell. The second image shows the portion of each sphere that lie inside the cube. The corners of the cube are shown with small circles labeled lattice points, and the phrase 8 corners is written below the image. Figure 10.49. A simple cubic lattice unit cell contains 1/8 of an atom at each of its 8 corners, so it contains 1 atom total. Example 10.14. Calculation of atomic radius and density for metals. Part 1. The edge length of the unit cell of alpha polonium is 336 pm. A. Determine the radius of a polonium atom. B. Determine the density of alpha polonium. Solution. Alpha polonium crystallizes in a simple cubic unit cell. A diagram shows a cube with a 1/8 portion of 8 spheres inside the cube, one section in each corner. Along the bottom right side of the cube are two double-ended arrows that each stretch along half of the total distance across the cube. Each arrow is labeled R. Two adjacent Po atoms contact each other, so the edge length of this cell is equal to 2 Po atomic radii. L equals 2R. Therefore, the radius of Po is letter 1d45f equals letter 1d4592 equals 336 pm2 equals 168 pm. B. Density is given by density equals mass volume. The density of polonium can be found by determining the density of its unit cell, the mass contained within a unit cell divided by the volume of the unit cell. Since a Po unit cell contains 1/8 of a Po atom at each of its 8 corners, a unit cell contains 1 Po atom. The mass of a Po unit cell can be found by 1 Po unit cell times 1 Po atom, 1 Po unit cell times 1 mol Po6. 0, 22 times 1023 Po atoms times 208. 998 G, 1 mol Po equals 3. 47 times 10 minus 22 G. The volume of a Po unit cell can be found by letter 1d449 equals letter 1d4593 equals 336 times 10 minus 10 cm 3 equals 3. 79 times 10 minus 23 cm 3. Note that the edge length was converted from pm to cm to get the usual volume units for density. Therefore, the density of Po equals 3. 471 times 10 minus 22 G3. 79 times 10 minus 23 cm3 equals 9. 16 G/cm3. Check your learning. The edge length of the unit cell for nickel is 0. 3524 nm. The density of Ni is 8. 90 G/cm3. Does nickel crystallize in a simple cubic structure? Explain. Answer: no. If Ni was simple cubic, its density would be given by 1 Ni atom times 1 mol Ni6. 0, 22 times 1023 Ni atoms times 58. 693 G, 1 mol Ni equals 9. 740, 6 times 10 minus 23 G. Letter 1d449 equals letter 1d4593 equals 3. 524 times 10 minus 8 cm3 equals 4. 376 times 10 minus 23 cm3. Then the density of Ni would be equals 9. 746 times 10 minus 23 G4. 376 times 10 minus 23 cm3 equals 2. 23 G/cm3. Since the actual density of Ni is not close to this, Ni does not form a simple cubic structure. Most metal crystals are one of the 4 major types of unit cells. For now, we will focus on the 3 cubic unit cells: simple cubic, which we have already seen, body-centered cubic unit cell, and face-centered cubic unit cell, all of which are illustrated in Figure 10.50. Note that there are actually 7 different lattice systems, some of which have more than one type of lattice, for a total of 14 different types of unit cells. We leave the more complicated geometries for later in this module. 3 pairs of images are shown. The first 3 images are in a row and are labeled lattice point locations, while the second 3 images are in a row labeled cubic unit cells. The first image in the top row shows a cube with black dots at each corner, while the first image in the second row is composed of 8 spheres that are stacked together to form a cube, and dots at the center of each sphere are connected to form a cube shape. The name under this image reads simple cubic. The second image in the top row shows a cube with black dots at each corner and a red dot in the center, while the second image in the second row is composed of 8 spheres that are stacked together to form a cube with 1 sphere in the center of the cube, and dots at the center of each corner sphere connected to form a cube shape. The name under this image reads body-centered cubic. The third image in the top row shows a cube with black dots at each corner and red dots in the center of each face, while the third image in the second row is composed of 8 spheres that are stacked together to form a cube with 6 more spheres located in the center of each face of the cube. Dots at the center of each corner sphere are connected to form a cube shape. The name under this image reads face-centered cubic. Figure 10. 50 cubic unit cells of metals show in the upper figures the locations of lattice points, and in the lower figures, metal atoms located in the unit cell. Some metals crystallize in an arrangement that has a cubic unit cell with atoms at all of the corners and an atom in the center, as shown in Figure 10. 51. This is called a body-centered cubic (BCC) solid. Atoms in the corners of a BCC unit cell do not contact each other, but contact the atom in the center. A BCC unit cell contains 2 atoms, 1/8 of an atom at each of the 8 corners. 8 times 18 equals 1 atom from the corners, plus 1 atom from the center. Any atom in this structure touches 4 atoms in the layer above it and 4 atoms in the layer below it. Thus, an atom in a BCC structure has a coordination number of 8. 3 images are shown. The first image shows a cube with black dots at each corner and a red dot in the center, while the second image is composed of 8 spheres that are stacked together to form a cube with 1 sphere in the center of the cube and dots at the center of each corner sphere connected to form a cube shape. The name under this image reads body-centered cubic structure. The third image is the same as the second, but only shows the portions of the spheres that lie inside the cube shape. Figure 10. 51. In a body-centered cubic structure, atoms in a specific layer do not touch each other. Each atom touches 4 atoms in the layer above it and 4 atoms in the layer below it. Atoms in BCC arrangements are much more efficiently packed than in a simple cubic structure, occupying about 68% of the total volume. Isomorphous metals with a BCC structure include K, Ba, Cr, Mo, W, and Fe at room temperature. Elements or compounds that crystallize with the same structure are said to be isomorphous. Many other metals, such as aluminum, copper, and lead, crystallize in an arrangement that has a cubic unit cell with atoms at all of the corners and at the centers of each face, as illustrated in Figure 10. 52. This arrangement is called a face-centered cubic FCC solid. A FCC unit cell contains 4 atoms, 1/8 of an atom at each of the 8 corners. 8 times 18 equals 1 atom from the corners, and 1/2 of an atom on each of the 6 faces. 6 times 12 equals 3 atoms from the faces. The atoms at the corners touch the atoms in the centers of the adjacent faces along the face diagonals of the cube. Because the atoms are on identical lattice points, they have identical environments. 3 images are shown. The first image shows a cube with black dots at each corner and red dots in the center of each face of the cube, while the second image is composed of 8 spheres that are stacked together to form a cube with 6 more spheres, one located on each face of the structure. Dots at the center of each corner sphere are connected to form a cube shape. The name under this image reads face-centered cubic structure. The third image is the same as the second, but only shows the portions of the spheres that lie inside the cube shape. Figure 10. 52. A face-centered cubic solid has atoms at the corners and, as the name implies, at the centers of the faces of its unit cells. Atoms in an FCC arrangement are packed as closely together as possible, with atoms occupying 74% of the volume. This structure is also called cubic closest packing, CCP. In CCP, there are 3 repeating layers of hexagonally arranged atoms. Each atom contacts 6 atoms in its own layer, 3 in the layer above, and 3 in the layer below. In this arrangement, each atom touches 12 near neighbors, and therefore has a coordination number of 12. The fact that FCC and CCP arrangements are equivalent may not be immediately obvious, but why they are actually the same structure is illustrated in Figure 10. 53. 3 images are shown. In the first image, a side view shows a layer of blue spheres, labeled C, stacked on top of, and sitting in between the gaps in a second layer that is composed of green spheres, labeled B, which are sitting atop a purple layer of spheres labeled A. A label below this image reads Side View. The second image shows a top view of the same layers of spheres, where the top layer is C, the second layer is B, and the lowest layer is C. This image is labeled Top View, and written under this is the phrase, Cubic Closest Packed Structure. The third image shows an upper view of the side of a cube composed of two sets of the repeating layers shown in the other images. The layers are arranged C, B, A, C, B, A, C, and the phrase written under this image reads Rotated View. Figure 10. 53. A CCP arrangement consists of three repeating layers, ABC, of hexagonally arranged atoms. Atoms in a CCP structure have a coordination number of 12 because they contact 6 atoms in their layer, plus 3 atoms in the layer above and 3 atoms in the layer below. By rotating our perspective, we can see that a CCP structure has a unit cell with a face containing an atom from layer A at one corner, atoms from layer B across a diagonal, at 2 corners and in the middle of the face, and an atom from layer C at the remaining corner. This is the same as a face-centered cubic arrangement. Because closer packing maximizes the overall attractions between atoms and minimizes the total intermolecular energy, the atoms in most metals pack in this manner. We find two types of closest packing in simple metallic crystalline structures, CCP, which we have already encountered, and hexagonal closest packing, HCP, shown in Figure 10.54. Both consist of repeating layers of hexagonally arranged atoms. In both types, a second layer B is placed on the first layer, A, so that each atom in the second layer is in contact with 3 atoms in the first layer. The third layer is positioned in one of two ways. In HCP, atoms in the third layer are directly above atoms in the first layer, i.e., the third layer is also type A, and the stacking consists of alternating type A and type B close-packed layers, i.e. ababab. In CCP, atoms in the third layer are not above atoms in either of the first 2 layers, i.e., the third layer is type C, and the stacking consists of alternating type A, type B, and type C close-packed layers, i.e. abcabcab. About 2/3 of all metals crystallize in closest packed arrays with coordination numbers of 12. Metals that crystallize in an HCP structure include CD, Co, Li, Mg, Na, and Zn. And metals that crystallize in a CCP structure include Ag, Al, Ka, Ku, Ni, Pb, and Pt. 2 images are shown. The first image, labeled hexagonal closest packed, shows 7 green spheres arranged in a circular sheet lying atop another sheet that is the same except the spheres are purple. The second sheet is offset just a bit so that the spheres of the top sheet lie in the grooves of the second sheet. 2 more alternating green and purple layers of spheres lie below the first pair. The second image shows 7 blue spheres, labeled Layer C, arranged in a circular sheet laying atop another sheet, labeled Layer B. That is the same except the spheres are green. The second sheet is offset just a bit so that the spheres of the top sheet lie in the grooves of the second sheet. 2 more alternating purple and then blue layers of spheres lie below the first pair. The purple layer is labeled Layer A, and the phrase written below this image reads, Cubic closest packed. Figure 10.54. In both types of closest packing, atoms are packed as compactly as possible. Hexagonal closest packing consists of 2 alternating layers, ABABAB. Cubic closest packing consists of 3 alternating layers, ABCABCBC. Example 10.15. Calculation of atomic radius and density for metals. Part 2. Calcium crystallizes in a face-centered cubic structure. The edge length of its unit cell is 558, 8 pm. A. What is the atomic radius of Ca in this structure? B. Calculate the density of Ca. Solution. An image of a cube is shown. A 1/8 section of a sphere is shown inside each corner of the cube, and a full sphere is shown in the middle of the cube. A line stretched across the front face of the cube from the top left corner to the bottom right corner is labeled 4R. The left and bottom sides of the cube are labeled A. In an FCC structure, Ka atoms contact each other across the diagonal of the face, so the length of the diagonal is equal to 4 Ka atomic radii, D equals 4R. Two adjacent edges and the diagonal of the face form a right triangle, with the length of each side equal to 558. 8 pm and the length of the hypotenuse equal to 4 Ka atomic radii. Letter 1d44e2 plus letter 1d44e2 equals letter 1d4512, 558. 8 pm 2 plus 558. 8 pm 2 equals 4 letter 1d45f2. Solving this gives letter 1d45f equals 558. 8 pm 2 plus 558. 8 pm 216 square equals 197. 6 pm for a Ka radius. B. Density is given by density equals mass volume. The density of calcium can be found by determining the density of its unit cell. For example, the mass contained within a unit cell divided by the volume of the unit cell. A face-centered Ka unit cell has 1/8 of an atom at each of the 8 corners. 8 times 18 equals 1. Atom and 1/2 of an atom on each of the 6 faces. 6 times 12 equals 3. Atoms for a total of 4 atoms in the unit cell. The mass of the unit cell can be found by 1 Ka unit cell times 4 Ka atoms 1 Ka unit cell times 1 mol Ka 6. 0, 22 times 1023 Ka atoms times 40. 78 G 1 mol Ka equals 2. 662 times 10 minus 22 G. The volume of a Ka unit cell can be found by letter 1d449 equals letter 1d44e3 equals 558. 8 times 10 minus 10 cm3 equals 1. 745 times 10 minus 22 cm3. Note that the edge length was converted from pm to cm to get the usual volume units for density. Then, the density of Ka equals 2. 662 times 10 minus 22 G1. 745 times 10 minus 22 cm3 equals 1. 53 G/cm3. Check your learning. Silver crystallizes in an FCC structure. The edge length of its unit cell is 409 pm. A. What is the atomic radius of Ag in this structure? B. Calculate the density of Ag. Answer. A. 144 pm. B. 10. 5 G/cm3. In general, a unit cell is defined by the lengths of 3 axes A, B, and C, and the angles alpha, beta, and gamma between them, as illustrated in Figure 10. 55. The axes are defined as being the lengths between points in the space lattice. Consequently, unit cell axes join points with identical environments. A cube is shown where each corner has a black dot drawn on it. A circle in the bottom of the cube is composed of 3 double-ended arrows. The left top of this circle is labeled alpha, the top right is labeled beta, and the bottom is labeled gamma. The bottom left corner of the cube is labeled A, while the bottom of the back face is labeled B, and the top back left corner is labeled C. Figure 10. 55. A unit cell is defined by the lengths of its 3 axes, A, B, and C, and the angles alpha, beta, and gamma between the axes. There are 7 different lattice systems, some of which have more than one type of lattice, for a total of 14 different unit cells, which have the shapes shown in Figure 10. 56. A table is composed of 2 columns and 8 rows. The header row reads system/axes/angles and unit cells. The first column reads cubic, A equals B equals C, alpha equals beta equals gamma equals 90 degrees. Tetragonal, A equals B does not equal C, Alpha equals beta equals gamma equals 90 degrees. Orthorhombic, A does not equal B does not equal C. Alpha equals beta equals gamma equals 90 degrees. Monoclinic, A does not equal B does not equal C. Alpha equals gamma equals 90 degrees. Beta does not equal 90 degrees. Triclinic, A does not equal B does not equal C. Alpha does not equal beta does not equal gamma does not equal 90 degrees. Hexagonal, A equals B does not equal C. Alpha equals beta equals 90 degrees. Gamma equals 120 degrees. Rhombohedral, A equals B equals C. Alpha equals beta equals gamma does not equal 90 degrees. The second column is composed of diagrams. The first set of diagrams in the first cell show a cube with spheres at each corner labeled simple, a cube with spheres in each corner and on each face labeled face-centered, and a cube with spheres in each corner and one in the center labeled body-centered. The second set of diagrams in the second cell show a vertical rectangle with spheres at each corner labeled simple, and a vertical rectangle with spheres in each corner and one in the center labeled body-centered. The third set of diagrams in the third cell show a vertical rectangle with spheres at each corner labeled simple, a vertical rectangle with spheres in each corner and one in the center labeled body-centered, a vertical rectangle with spheres in each corner and one on the top and bottom faces labeled base-centered, and a vertical rectangle with spheres in each corner and one on each face labeled face-centered. The fourth set of diagrams in the fourth cell show a vertical rectangle with spheres at each corner that is slanted to one side labeled simple, and a vertical rectangle with spheres in each corner that is slanted to one side and has two spheres in the center is labeled body-centered. The fifth diagrams in the fifth cell show a cube that is slanted with spheres at each corner, while the sixth diagram in the sixth cell shows a pair of hexagonal rings that are connected together to form a six-sided shape with spheres at each corner. The seventh diagram in the seventh cell shows a rectangle that is slanted with spheres at each corner. Figure 10. 56. There are 7 different lattice systems and 14 different unit cells. The structures of ionic crystals. Ionic crystals consist of 2 or more different kinds of ions that usually have different sizes. The packing of these ions into a crystal structure is more complex than the packing of metal atoms that are the same size. Most monatomic ions behave as charged spheres, and their attraction for ions of opposite charge is the same in every direction. Consequently, stable structures for ionic compounds result: 1. When ions of one charge are surrounded by as many ions as possible of the opposite charge, and 2. When the cations and anions are in contact with each other. Structures are determined by 2 principal factors: the relative sizes of the ions and the ratio of the numbers of positive and negative ions in the compound. In simple ionic structures, we usually find the anions, which are normally larger than the cations, arranged in a closest packed array. As seen previously, additional electrons attracted to the same nucleus make anions larger and fewer electrons attracted to the same nucleus make cations smaller when compared to the atoms from which they are formed. The smaller cations commonly occupy one of 2 types of holes, or interstices, remaining between the anions. The smaller of the holes is found between 3 anions in one plane and 1 anion in an adjacent plane. The 4 anions surrounding this hole are arranged at the corners of a tetrahedron, so the hole is called a tetrahedral hole. The larger type of hole is found at the center of 6 anions, 3 in one layer and 3 in an adjacent layer, located at the corners of an octahedron. This is called an octahedral hole. Figure 10. 57 illustrates both of these types of holes. An image shows a top view of a layer of blue spheres arranged in a sheet lying atop another sheet that is the same except the spheres are green. The second sheet is offset just a bit so that the spheres of the top sheet lie in the grooves of the second sheet. A third sheet composed of purple spheres lies at the bottom. The spaces created between the spheres in each layer are labeled octahedral holes and tetrahedral holes. Figure 10. 57 cations may occupy two types of holes between anions: octahedral holes or tetrahedral holes. Depending on the relative sizes of the cations and anions, the cations of an ionic compound may occupy tetrahedral or octahedral holes, as illustrated in Figure 10. 58. Relatively small cations occupy tetrahedral holes, and larger cations occupy octahedral holes. If the cations are too large to fit into the octahedral holes, the anions may adopt a more open structure, such as a simple cubic array. The larger cations can then occupy the larger cubic holes made possible by the more open spacing. A diagram of three images is shown. In the first image, 8 stacked cubes with purple spheres at each corner that make up one large cube are shown. The bottom left cube is different. It has green spheres at each corner and has 4 orange and 6 light purple spheres located on the faces of the cube. Labels below this structure read tetrahedral hole, and cation radius is about 22. 5 to 41, 4% of the anion radius. In the second image, 8 stacked cubes with alternating orange and green spheres at each corner make up one large cube that is shown. The bottom left cube has darker lines that connect the spheres together. Labels below this structure read octahedral hole, and cation radius is about 41.4 to 73, 2% of the anion radius. In the third image, 8 stacked cubes, with purple spheres at each corner and light purple spheres on their interior faces, make up one large cube that is shown. Labels below this structure read cubic hole, and cation radius is about 73, 2 to 100% of the anion radius. Figure 10. 58. A cation's size and the shape of the hole occupied by the compound are directly related. There are 2 tetrahedral holes for each anion in either an HCP or CCP array of anions. A compound that crystallizes in a closest packed array of anions with cations in the tetrahedral holes can have a maximum cation ratio of 2:1. All of the tetrahedral holes are filled at this ratio. Examples include Li2O, Nut2O, Li2S, and Nut2S compounds with a ratio of less than 2. One may also crystallize in a closest packed array of anions with cations in the tetrahedral holes, if the ionic sizes fit. In these compounds, however, some of the tetrahedral holes remain vacant. Example 10, 16. Occupancy of tetrahedral holes. Zinc sulfide is an important industrial source of zinc, and is also used as a white pigment in paint. Zinc sulfide crystallizes with zinc ions occupying 1/2 of the tetrahedral holes in a closest packed array of sulfide ions. What is the formula of zinc sulfide? Solution: because there are 2 tetrahedral holes per anion sulfide ion, and 1/2 of these holes are occupied by zinc ions, there must be 12 times 2, or 1 zinc ion per sulfide ion. Thus the formula is ZnS. Check your learning. Lithium selenide can be described as a closest packed array of selenide ions with lithium ions in all of the tetrahedral holes. What is the formula of lithium selenide? Answer: Lita C. The ratio of octahedral holes to anions in either an HCP or CCP structure is 1:1. Thus, compounds with cations in octahedral holes in a closest packed array of anions can have a maximum cation ratio of 1:1 in NiO, MnS, NaCl, and Kh. For example, all of the octahedral holes are filled. Ratios of less than 1:1 are observed when some of the octahedral holes remain empty. Example 10, 17. Stoichiometry of ionic compounds. Sapphire is aluminum oxide. Aluminum oxide crystallizes with aluminum ions in 2/3 of the octahedral holes in a closest packed array of oxide ions. What is the formula of aluminum oxide? Solution: because there is 1 octahedral hole per anion oxide ion, and only 2/3 of these holes are occupied. The ratio of aluminum to oxygen must be 23:1, which would give Al2/30. The simplest whole number ratio is 2:3, so the formula is Al2O3. Check your learning. The white pigment titanium oxide crystallizes with titanium ions in one half of the octahedral holes in a closest packed array of oxide ions. What is the formula of titanium oxide? Answer: TO2. In a simple cubic array of anions, there is one cubic hole that can be occupied by a cation for each anion in the array. In CsCl and in other compounds with the same structure, all of the cubic holes are occupied. Half of the cubic holes are occupied in SrH2, UO2, SrCl2, and KF2. Different types of ionic compounds often crystallize in the same structure when the relative sizes of their ions and their stoichiometries, the two principal features that determine structure, are similar. Unit cells of ionic compounds. Many ionic compounds crystallize with cubic unit cells, and we will use these compounds to describe the general features of ionic structures. When an ionic compound is composed of cations and anions of similar size in a 1:1 ratio, it typically forms a simple cubic structure. Cesium chloride, CsCl, illustrated in Figure 10:59, is an example of this, with Cs plus and Cl minus having radii of 174 pm and 181 pm, respectively. We can think of this as chloride ions forming a simple cubic unit cell, with a cesium ion in the center, or as cesium ions forming a unit cell with a chloride ion in the center, or as simple cubic unit cells formed by Cs plus ions, overlapping unit cells formed by Cl minus ions. Cesium ions and chloride ions touch along the body diagonals of the unit cells. One cesium ion and one chloride ion are present per unit cell, giving the 1:1 stoichiometry required by the formula for cesium chloride. Note that there is no lattice point in the center of the cell, and CsCl is not a BCC structure because a cesium ion is not identical to a chloride ion. 3 images are shown. The first image shows a cube with black dots at each corner and a red dot in the center. This cube is stacked with 7 others that are not colored to form a larger cube. The second image is composed of 8 spheres that are grouped together to form a cube with one smaller sphere in the center. The name under this image reads simple cubic structure. The third image shows 5 horizontal layers of purple spheres with layers of smaller green spheres in between. Figure 10:59 ionic compounds with similar-sized cations and anions, such as CsCl, usually form a simple cubic structure. They can be described by unit cells with either cations at the corners or anions at the corners. We have said that the location of lattice points is arbitrary. This is illustrated by an alternate description of the CsCl structure, in which the lattice points are located in the centers of the cesium ions. In this description, the cesium ions are located on the lattice points at the corners of the cell, and the chloride ion is located at the center of the cell. The two unit cells are different, but they describe identical structures. When an ionic compound is composed of a 1:1 ratio of cations and anions that differ significantly in size, it typically crystallizes with an FCC unit cell, like that shown in Figure 10:60. Sodium chloride, NaCl, is an example of this, with Na plus and Cl minus having radii of 102 pm and 181 pm, respectively. We can think of this as chloride ions forming an FCC cell, with sodium ions located in the octahedral holes in the middle of the cell edges and in the center of the cell. The sodium and chloride ions touch each other along the cell edges. The unit cell contains 4 sodium ions and 4 chloride ions, giving the 1:1 stoichiometry required by the formula NaCl. 3 images are shown. The first image shows a cube with black dots at each corner and a red dot in the center. This cube is stacked with 7 others that are not colored to form a larger cube. The second image is composed of 8 spheres that are grouped together to form a cube with one much larger sphere in the center. The name under this image reads Body-Centered Simple Cubic Structure. The third image shows 7 horizontal layers of alternating purple and green spheres that are slightly offset with one another and form a large cube. Figure 10. 60 ionic compounds with anions that are much larger than cations, such as NaCl, usually form an FCC structure. They can be described by FCC unit cells with cations in the octahedral holes. The cubic form of zinc sulfide, zinc blende, also crystallizes in an FCC unit cell, as illustrated in Figure 10. 61. This structure contains sulfide ions on the lattice points of an FCC lattice. The arrangement of sulfide ions is identical to the arrangement of chloride ions in sodium chloride. The radius of a zinc ion is only about 40% of the radius of a sulfide ion, so these small Zn2 plus ions are located in alternating tetrahedral holes, that is, in one half of the tetrahedral holes. There are 4 zinc ions and 4 sulfide ions in the unit cell, giving the empirical formula ZnS. 2 images are shown. The first image shows a cube with black dots at each corner and a red dot in the center of each face of the cube. This cube is stacked with 7 others that are not colored to form a larger cube. The second image is composed of 8 spheres that form the corners of a cube with 6 other spheres located in the face of the cube. The spheres are connected to one another by lines. The name under this image reads ZnS, face-centered unit cell. Figure 1061 ZnS, zinc sulfide, or zinc blende, forms an FCC unit cell with sulfide ions at the lattice points and much smaller zinc ions occupying half of the tetrahedral holes in the structure. A calcium fluoride unit cell, like that shown in Figure 10. 62, is also an FCC unit cell, but in this case, the cations are located on the lattice points. Equivalent calcium ions are located on the lattice points of an FCC lattice. All of the tetrahedral sites in the FCC array of calcium ions are occupied by fluoride ions. There are 4 calcium ions and 8 fluoride ions in a unit cell, giving a calcium-fluorine ratio of 1:2, as required by the chemical formula Kf2. Close examination of Figure 10. 62 will reveal a simple cubic array of fluoride ions with calcium ions in one half of the cubic holes. The structure cannot be described in terms of a space lattice of points on the fluoride ions, because the fluoride ions do not all have identical environments. The orientation of the 4 calcium ions about the fluoride ions differs. 2 images are shown. The first image shows a cube with black dots at each corner and a red dot in the center of each face of the cube. This cube is stacked with 7 others that are not colored to form a larger cube. The second image is composed of 8 small green spheres that form the corners of a cube, with 6 other small green spheres located in the faces of the cube. 8 larger green spheres are spaced inside the cube, and all of the spheres are connected to one another by lines. The name under this image reads CF, subscript 2, face-centered unit cell. Figure 10. 62 calcium fluoride, Kf2, forms an FCC unit cell with calcium ions green at the lattice points and fluoride ions red, occupying all of the tetrahedral sites between them. Calculation of ionic radii. If we know the edge length of a unit cell of an ionic compound and the position of the ions in the cell, we can calculate ionic radii for the ions in the compound if we make assumptions about individual ionic shapes and contacts. Example 10.18. Calculation of ionic radii. The edge length of the unit cell of LiCl, NaCl-like structure, FCC is 0.514 nm or 514 A ring. Assuming that the lithium ion is small enough so that the chloride ions are in contact, as in Figure 10. 60, Calculate the ionic radius for the chloride ion. Note: the length unit angstrom, A ring, is often used to represent atomic scale dimensions and is equivalent to 10-10 m solution. On the face of a Li-Cl unit cell, chloride ions contact each other across the diagonal of the face. 3 images are shown. The first shows a cube of alternating green and purple spheres. A smaller cube within that cube is outlined, and a larger version of it appears next. This figure is a gray cube that appears to be made up of spheres. There are small spaces between each sphere. There is a right triangle outlined in this cube, and a larger version of it appears next. This right triangle has 2 sides labeled A, and the hypotenuse, which spans 2 half circles and 1 full one, is labeled R, 2R, and R. Drawing a right triangle on the face of the unit cell, we see that the length of the diagonal is equal to 4 chloride radii, 1 radius from each corner chloride and 1 diameter, which equals 2 radii from the chloride ion in the center of the face. So D equals 4R. From the Pythagorean theorem, we have letter 1d4 4e2 plus letter 1d4 4e2 equals letter 1d4 512, which yields 0, 514 nm2 plus 0, 514 nm2 equals 4 letter 1d4 5f2 equals 16 letter 1d4 5f2. Solving this gives letter 1d4 5f equals 0, 514 nm2 plus 0, 514 nm 216 square equals 0, 182 nm 1, 82 a ring for a Cl minus radius. Check your learning. The edge length of the unit cell of KCl, NaCl-like structure, FCC, is 6. 28 a ring. Assuming anion and cation contact along the cell edge, calculate the radius of the potassium ion. The radius of the chloride ion is 1. 82 a ring. Answer: the radius of the potassium ion is 1. 33 a ring. It is important to realize that values for ionic radii calculated from the edge lengths of unit cells depend on numerous assumptions, such as a perfect spherical shape for ions, which are approximations at best. Hence, such calculated values are themselves approximate, and comparisons cannot be pushed too far. Nevertheless, this method has proved useful for calculating ionic radii from experimental measurements such as X-ray crystallographic determinations. X-ray crystallography, the size of the unit cell and the arrangement of atoms in a crystal, may be determined from measurements of the diffraction of X-rays by the crystal, termed X-ray crystallography. Diffraction is the change in the direction of travel experienced by an electromagnetic wave when it encounters a physical barrier, whose dimensions are comparable to those of the wavelength of the light. X-rays are electromagnetic radiation with wavelengths about as long as the distance between neighboring atoms in crystals, on the order of a few A-ring. When a beam of monochromatic X-rays strikes a crystal, its rays are scattered in all directions by the atoms within the crystal. When scattered waves traveling in the same direction encounter one another, they undergo interference, a process by which the waves combine to yield either an increase or a decrease in amplitude, intensity, depending upon the extent to which the combining waves, maxima, are separated. See Figure 10. 63. A pair of images is shown that has 4 sections. In the first section, 2 sinusoidal waves are shown, one drawn above the other, and a section from the top of one curve to the top of the next curve is labeled lambda. The curves align with one another. The phrase below this reads constructive interference. A right-facing arrow leads from the first section to the second, which shows one larger sinusoidal curve that has higher and lower peaks and troughs. A section from the top of one curve to the top of the next curve is labeled lambda, and the phrase below this reads maxima and minima reinforce. In the second section, 2 sinusoidal waves are shown, one drawn above the other, and a section from the top of one curve to the top of the next curve is labeled lambda. The curves do not align with one another. The phrase below this reads destructive interference. A right-facing arrow leads from the first section to the second, which shows one flat line. The phrase below this reads maxima and minima cancel. Figure 10. 63 light waves occupying the same space experience interference, combining to yield waves of greater A or lesser B intensity, depending upon the separation of their maxima and minima. When X-rays of a certain wavelength lambda are scattered by atoms in adjacent crystal planes separated by a distance d, they may undergo constructive interference when the difference between the distances traveled by the two waves prior to their combination is an integer factor, n, of the wavelength. This condition is satisfied when the angle of the diffracted beam, theta, is related to the wavelength and intraatomic distance by the equation. Letter 1D45B letter 1D70. 6 equals 2 letter 1D451, SI n letter 1D703. This relation is known as the Bragg equation in honor of W. H. Bragg, the English physicist who first explained this phenomenon. Figure 10. 64 illustrates two examples of diffracted waves from the same two crystal planes. The figure on the top depicts waves diffracted at the Bragg angle, resulting in constructive interference, while that on the bottom shows diffraction and a different angle that does not satisfy the Bragg condition, resulting in destructive interference. Two similar figures are shown. The first figure, labeled constructive interference, shows two horizontal rows of 7 black dots with a line passing through them. The fourth dots of each row have a vertical line connecting them. The distance between these rows is labeled d. A beam labeled incident beam descends at an angle labeled theta until it hits the line connecting the fourth dots, after which a diffracted beam ascends at the same angle theta. A dotted line is drawn across the diffracted beam. The second figure, labeled destructive interference, is very similar except that the angles theta are far more acute, making the slopes of the beams more shallow. Figure 10. 64. The diffraction of X-rays scattered by the atoms within a crystal permits the determination of the distance between the atoms. The top image depicts constructive interference between two scattered waves and a resultant diffracted wave of high intensity. The bottom image depicts destructive interference and a low-intensity diffracted wave. Link to learning. Visit this site for more details on the Bragg equation and a simulator that allows you to explore the effect of each variable on the intensity of the diffracted wave. An X-ray diffractometer, such as the one illustrated in Figure 10. 65, may be used to measure the angles at which X-rays are diffracted when interacting with a crystal, as described earlier. From such measurements, the Bragg equation may be used to compute distances between atoms as demonstrated in the following example exercise. A diagram, labeled A, shows a cube on the left with a channel bored into its right side labeled X-ray source. A beam is leaving from this channel and traveling in a horizontal line toward an oval-shaped, short tube, labeled collimator to focus beam, an X-ray diffraction, where it passes through a cube labeled crystalline material and scatters onto a vertical sheet labeled imaging surface. A second diagram, labeled B, shows a square sheet with a large dot in the center labeled X-ray beam that is surrounded by smaller dots arranged in rings and labeled diffracted X-rays. Figure 10. 65a. In a diffractometer, a beam of X-rays strikes a crystalline material, producing B, an X-ray diffraction pattern that can be analyzed to determine the crystal structure. Example 10. 19. Using the Bragg equation. In a diffractometer, X-rays with a wavelength of 0.1315 nm were used to produce a diffraction pattern for copper. The first-order diffraction, n equals 1, occurred at an angle theta equals 25 degrees. Determine the spacing between the diffracting planes in copper. Solution. The distance between the planes is found by solving the Bragg equation and lambda equals 2d sin theta. For d this gives letter 1d451 equals letter 1d45b letter 1d706 to s. In letter 1d703 equals 1315 nm, 2 sin 25 degrees, 154 nm. Check your learning. A crystal with spacing between planes equal to 0. 394 nm diffracts X-rays with a wavelength of 0. 147 nm. What is the angle for the first-order diffraction? Answer: 10. 8 degrees. Portrait of a chemist. X-ray crystallographer Rosalind Franklin. The discovery of the structure of DNA in 1953 by Francis Crick and James Watson is one of the great achievements in the history of science. They were awarded the 1962 Nobel Prize in Physiology or Medicine, along with Maurice Wilkins, who provided experimental proof of DNA structure. British chemist Rosalind Franklin made invaluable contributions to this monumental achievement through her work in measuring X-ray diffraction images of DNA. Early in her career, Franklin's research on the structure of coals proved helpful to the British war effort. After shifting her focus to biological systems in the early 1950s, Franklin and doctoral student Raymond Gosling discovered that DNA consists of two forms: a long, thin fiber formed when wet type B, and a short, wide fiber formed when dried type A. Her X-ray diffraction images of DNA, figure 10.66, provided the crucial information that allowed Watson and Crick to confirm that DNA forms a double helix and to determine details of its size and structure. Franklin also conducted pioneering research on viruses and the RNA that contains their genetic information, uncovering new information that radically changed the body of knowledge in the field. After developing ovarian cancer, Franklin continued to work until her death in 1958 at age 37. Among many posthumous recognitions of her work, the Chicago Medical School of Finch University of Health Sciences changed its name to the Rosalind Franklin University of Medicine and Science in 2004 and adopted an image of her famous X-ray diffraction image of DNA as its official university logo. An image shows a circular illustration with rings of dots that are blurred together. Figure 10.66. This illustration shows an X-ray diffraction image similar to the one Franklin found in her research. Credit: National Institutes of Health.